Hello there, and welcome to Drift to the Stars. I'm so glad you found your way here tonight. Tonight we travel to the edge of what light can reach, and just beyond it. To places where time bends, where silence has weight, and where the universe keeps its most carefully guarded secrets. If tonight's journey brings you some peace or wonder, or simply a good night's rest, please consider sharing it with someone who might need the same. A like or a share takes a moment, and it helps others find their way here too. Now if you're ready, let's begin. There is something in the universe that is not quite what its name suggests. We call it a black hole, and for decades that name conjured something like a drain, a dark mouth pulling everything down into nothing. But a black hole is not an absence, it is a presence. A concentration of gravity so complete, so patient, so total, that even the fabric of space curves around it the way a heavy stone curves the surface of still water. It is not a hole. It is the universe at its most serious. A place where mass has folded inward until the normal rules of distance and time no longer apply in the way we expect them to. Gravity, that familiar pull that keeps your feet on the floor and the moon in its path, is simply the shape of space near mass. A black hole is what happens when mass becomes so concentrated that the shape of space becomes inescapable. Not violent, not angry, just complete. And there are billions of them drifting through the dark ancient and still doing what gravity has always done, quietly, holding everything together. Somewhere between the star and the darkness there is a line. It has no color, no texture, no wall, no gate, no shimmer in the light. You could not see it if you passed through it. You could not feel it underfoot. And yet it is the most consequential boundary in the known universe. It is called the event horizon, the edge beyond which nothing, not even light, can turn around and find its way back. The word horizon is exactly right in a quiet way. A horizon on Earth is not a real boundary either. It is simply the limit of what your position allows you to see. The event horizon of a black hole works the same way, except that crossing it changes what is possible, not just what is visible. General relativity, the framework that describes gravity at its deepest level, tells us that the event horizon is woven into the geometry of space-time itself. It is a feature of the shape of the universe, near extreme mass, not a surface you could touch, but a point of no return, embedded in the structure of space. Once crossed, the future has only one direction. Not forward through time in the usual sense, but inward, toward the center. Always inward. The universe draws certain lines quietly. This is the quietest of all. Picture someone you trust. Imagine watching them from a great safe distance as they float slowly toward the edge of a black hole. You have a telescope, fine enough to see everything. You watch, and you wait. And here is what you see. They slow down. Gradually then, more gradually still. Their movements become languid, like someone settling into deep water. The light reaching you from their body stretches, shifts toward red, grows dimmer. And then they appear to stop, hovering at the edge, frozen, caught in the last moment before crossing. They never seem to arrive. This is not a trick of your imagination. It is a real consequence of how gravity bends time. The closer you are to an intense gravitational field, the more slowly time passes for you, relative to someone farther away. Near the event horizon, that effect becomes extreme. From your distant vantage point, the person appears to slow to a halt, their image fading and reddening as the light from their body struggles to climb out of the gravity well. This is called gravitational time dilation. It has been measured and confirmed here on Earth, near our own planet's modest gravity, using atomic clocks at different altitudes. What you would see at the edge of a black hole is simply that same effect, taken to its most profound conclusion. The edge from the outside holds everything at the last moment, forever. And yet, for the one falling in, nothing announces itself. No siren, no shudder, no darkening of the light. If the black hole is large enough, the person crossing the event horizon might feel nothing unusual at all in that moment. No jolt, no warning. The physics of their immediate surroundings, the air around them, the feeling of their own body would be entirely ordinary. This is one of the quieter astonishments of black hole physics. The most absolute boundary in the universe is also experientially the most invisible. General relativity tells us that what matters near the horizon is the tidal force, the difference in gravity between your head and your feet. For a stellar mass black hole, that difference is enormous and would be lethal long before the crossing. But for a truly massive black hole, 1 billions of times heavier than the Sun, the event horizon is so large that the tidal forces at the edge are gentle. Crossing would feel like floating. You would only know you had crossed it because looking outward you would see that light from the universe beyond was still reaching you, but you could no longer send any signal back. Communication in one direction only. Receiving but no longer able to reply. There is something quietly poignant in that. To be surrounded by the light of the whole universe, and to know that your own light can no longer reach it. The universe contains multitudes, and black holes are no different. At one end of their range sit the smallest objects theoretically possible, though never yet confirmed, so compact that something with the mass of a mountain would fit within a space far smaller than a single atom. These are called primordial or micro black holes, and they belong mostly to the realm of theory, mathematical solutions, waiting to be found or not found in the data. What has been confirmed is that stellar mass black holes, the kind born when massive stars collapse, range from roughly 5 to several tens of times the mass of the Sunday. That may sound large, but squeezed into a black hole, that mass occupies a region perhaps 30 kilometers across, the width of a small city, less than the distance many people drive to work. Hold that image for a moment. The mass of several suns, the width of a city you could cross in half an hour by car. Gravity compresses matter so thoroughly that the familiar relationship between how much something weighs and how much space it occupies simply breaks down. A teaspoon of neutron star material, the dense remnant that sometimes precedes black hole formation, would weigh roughly as much as a mountain range. And a black hole takes that density further still. It takes it all the way to the place where our measuring tools run out of words. Now consider the other end. These are the black holes, called ultramassive, a name that does not quite do them justice, but no word truly could. They sit at the centers of the largest galaxies, and some of them have grown to masses of tens of billions of times that of the Sunday. The largest confirmed black hole known sits at the center of a galaxy called TON 618. And its mass is estimated at roughly 66 billion solar masses. The event horizon of such an object would be so wide that if you placed our solar system at the center, the edge of the horizon would stretch far beyond the farthest reaches of the planets, past the distant belt of icy bodies at the outermost edge of our sun's family. Light traveling at the fastest speed anything can travel in this universe would take weeks to cross from one side of that event horizon to the other. Even now, as you breathe quietly wherever you are, that object exists sitting at the heart of its galaxy, ancient, and still having spent billions of years becoming what it is through patient accumulation. Weeks for light to cross one object. The universe does not do modesty when it commits to something. People sometimes imagine a black hole as a kind of cosmic vacuum cleaner, endlessly hungry, sucking everything nearby into itself, a danger to anything that comes close. This is not how gravity works, and black holes obey gravity like everything else. A black hole pulls on nearby objects exactly as any other mass of the same size would pull. It is not greedier. It does not reach out further. It does not pull harder simply because it is a black hole. The gravity of a black hole at a given distance is identical to the gravity of any other object of the same mass at that same distance. The difference is only that you can get much closer to a black hole before being swallowed, because there is no surface to stop you. A star with the same mass would have an enormous radius, and you would hit its outer layers long before reaching the concentrated core. A black hole has no such surface. You can fall all the way in, but from far away a black hole is gravitationally no more dangerous than a star of the same mass. If you kept a safe distance, you would orbit it peacefully, just as planets orbit stars. Gravity is patient. It does not chase. It simply shapes the space around it and waits for whatever time and trajectory bring near. There is something almost restful in that once you understand it. To understand that truth a little more gently, consider our own Sunday. One day, billions of years from now, after the sun has expanded into a red giant and shed its outer layers, what remains may be a white dwarf, a dense remnant, but not a black hole. The sun is not quite massive enough for that final collapse. But suppose for a thought experiment that the sun was somehow replaced overnight by a black hole of exactly the same mass. Not larger, not denser in any gravitational sense at a distance. The same mass in a much smaller space. What would happen to Earth? Nothing, or rather nothing immediately alarming. Earth would continue along its orbit at the same speed, at the same distance, following the same curved path through space it has always followed. The gravitational influence at Earth's distance would be identical, because the mass would be identical. We would of course lose our warmth and our light. The sky would go dark. Life as it exists would not survive the cold, but we would not be pulled in. We would not spiral toward doom. We would simply orbit quietly in the dark, around a point of invisible gravity, exactly as we orbit now around a visible one. What the sun gives us is not just gravity. It is light and heat, and the slow, patient energy that makes life possible. A black hole of the same mass would give us only the first. For a long time, they were only mathematics. In 1916, just 1 year after Einstein published his general theory of relativity, a German physicist and soldier named Karl Schwarzschild solved the equations from the trenches of the Eastern Front while the war continued around him, and found that they allowed for a strange object, a mass, compressed so completely that space closed around it. He sent his solution to Einstein. Einstein was reportedly surprised it had been found so quickly. Schwarzschild died months later of an illness contracted at the front. His solution described what we now call a black hole. But for decades, the idea was treated as a mathematical curiosity, an extreme case that the universe would never actually produce. Physicists, including Einstein himself, assumed that some natural process would always intervene to prevent such total collapse. The universe, it turned out, had no such reservations. By the middle of the 20th century, evidence began accumulating. Stars were being observed that seemed to be orbiting invisible, enormously massive companions. X-ray sources were discovered that could only be explained by matter falling into objects of extreme density. The mathematics had been waiting, patient and correct, for decades. Reality simply took its time, arriving at the same conclusion. Sometimes the equations know before the evidence does. On the 11th of April 2019, something unprecedented happened. A collaboration called the Event Horizon Telescope released the first direct image of a black hole, specifically the one at the center of a galaxy called M87, roughly 55 million light-years away. The image showed a glowing orange and red ring of superheated gas, with a dark circular shadow at its center. To take that image, a team of over 200 scientists linked together radio telescopes spread across the entire surface of the Earth, in Hawaii, in Chile, in Spain, in Greenland, in Antarctica, and elsewhere. The telescopes were synchronized so precisely that they effectively acted as a single dish as wide as the planet itself. The data collected was so enormous that it could not be transmitted over the internet. It had to be recorded onto hard drives and physically shipped to processing centers where algorithms assembled the image over many months. No single telescope could have done it. No single country. No single generation of technology. It took the whole planet, working as one, pointing together in the same direction, to see a thing that emits no light of its own, only the glow of what surrounds it. There is something in that image that goes beyond astronomy. Something about what becomes visible when enough of us pay attention in the same direction at the same time. Clocks do not all tick at the same rate. This is not a poetic idea. It is a measured, confirmed, practical fact. One that engineers who design navigation satellites must account for in their calculations, or the maps on your phone would drift off by kilometers every single day. Time passes more slowly in stronger gravitational fields. The closer you are to a massive object, the more gravity curves the fabric of space-time around you, and the more slowly your clock ticks relative to someone sitting farther away in weaker gravity. Near the surface of the Earth, this effect is small but real. A clock on the ground ticks very slightly more slowly than a clock on a satellite in orbit. The difference is measured in microseconds per day, tiny, but enough to matter for precision systems. Now carry that same effect toward a black hole. As you move closer, gravity intensifies. The ticking slows. Further still, and it slows more dramatically. At the event horizon itself, from the perspective of a distant observer, time appears to stop altogether. This is not an illusion. It is not a trick of perception. It is the geometry of the universe doing exactly what the equations say it should. Time, that most intimate and personal of experiences, the rhythm of your heartbeat, the turning of your thoughts as you drift towards sleep, is not fixed. It bends. It responds to the shape of space around it. And somewhere in the universe tonight, a clock is ticking so slowly it has barely moved since the Earth was young. Two clocks, both perfectly made, both set to the same time. One stays with you wherever you are right now, on a table beside your bed or on the wall across the room. The other is carried to the edge of a black hole, held there for what feels to the carrier like a single quiet hour, and then brought back. When they are placed side by side again, they will not agree. The clock that traveled near the black hole will show less time has passed. Not because it was damaged, not because the journey jostled its mechanism, but because time itself moved differently there. The carrier aged less, their heartbeats were fewer. Their thoughts unfolded more slowly, not from the inside. From the inside, everything felt perfectly ordinary, but relative to you, waiting far away. This is called gravitational time dilation, and it has been confirmed not only near black holes in theory, but right here on Earth in practice. Physicists have carried extremely precise atomic clocks up mountains and compared them to identical clocks left at sea level. The clocks at higher altitude, where gravity is very slightly weaker, run measurably faster. General relativity predicted this in 1915. The measurements confirmed it decades later. Both clocks are always correct. They are simply each telling the truth about the time where they are. The universe does not keep one universal clock. It keeps billions, one for every place and every speed, and they all tell different stories. Around a black hole, where you might expect only darkness, there is light. Not from the black hole itself, nothing escapes from within the event horizon, but in the space just outside, gas and dust, and the remnants of torn-apart stars gather and begin to spiral inward. As they spiral, they compress. As they compress, they heat. And as they heat, they glow. The temperatures reached in this infalling material, called an accretion disk, are extraordinary. Not the warmth of a hearth, not the heat of the sun's surface, but temperatures of millions of degrees, hot enough to emit not just visible light but X-rays, the same radiation used to see through the human body in a hospital. The disk glows in rings, brighter toward the center, where the material moves fastest and heats most intensely. Because of the black hole's enormous gravity, light from the back of the disk bends around toward you, so you can see both the top of the disk and a portion of its far side curving around like the brim of a hat. The shape is not what you might expect. It is not simply a flat ring. It is layered, curved, wrapped around itself by gravity in a way that no other object in the universe produces. And it is warm. Against the cold of space, against the darkness of the void, the accretion disk glows steadily, a fire kept burning not by chemistry but by gravity and by the long patience of infalling matter. That quiet fire can become something far from quiet. When a black hole is feeding actively, when the flow of infalling material is rich and fast, the accretion disk can reach a luminosity that strains the imagination. A single, actively feeding black hole at the center of a galaxy in a phase called a quasar or active galactic nucleus can pour out more light than all the stars in the galaxy surrounding it combined, more light than hundreds of billions of stars from one object, smaller in some cases than our solar system. The energy source is gravity. As matter falls toward the black hole, it loses gravitational potential energy, and much of that energy is converted to heat and light before the material ever crosses the horizon. In fact, this process is among the most efficient energy conversion mechanisms known in physics. Far more efficient than nuclear fusion, the process that powers the sunday. A small fraction of the infalling material, converted by gravity's compression into pure radiant energy, can outshine an entire galaxy. And yet the black hole at the center of our own galaxy is right now doing almost none of this. Sagittarius A star, as it is called, is dim and quiet. It flickers, occasionally brightening briefly when a small cloud of gas drifts close enough to be heated. But mostly, it simply waits. Our galaxy's heart is calm. And because it is calm, the sky above us is dark enough to see the stars. Not far from the center of everything you call home, something ancient waits. At the heart of the Milky Way, hidden behind thick clouds of gas and dust that block visible light, sits Sagittarius A star. It is a black hole with a mass of roughly 4 million times that of the Sun, what astronomers call a supermassive black hole, sitting at the gravitational center of our galaxy. 4 million solar masses. It is a number that resists direct feeling. So consider instead this image. The stars closest to it, a cluster of young blue stars, called the star's orbit Sagittarius A star, so closely and so fast that one of them, called Stu, completes a full orbit in just about 16 years. A star completing a full orbit around the center of a galaxy in 16 years. For comparison, our own Sun takes roughly 230 million years to complete one orbit around the galactic center. The gravity near Sagittarius A star is so intense that it shapes the motion of stars like a hand shaping the path of water in a stream. And this object is not some unimaginably distant thing. On the scale of the galaxy, it is nearby, 26,000 light-years away, which in cosmic terms is the distance to the next town. It has always been there since long before the Earth formed, since long before the Sun ignited. The center of your galaxy, holding everything together, always there just behind the dust. Right now, Sagittarius A star is resting. For most of its existence, our galaxy's central black hole has alternated between periods of activity and periods of deep quiet. Right now, and for the last several million years, it is in one of its quiet phases. The flow of material falling into it is slow. The accretion disk is dim. The jets that sometimes shoot from the poles of active black holes are largely absent. This is unusual compared to many galaxies. The central black holes of other galaxies, even some not much larger than the Milky Way, are blazing with activity, pouring radiation across space, shaping the evolution of their host galaxies through the sheer force of what they release. Ours is sleeping, and that matters for us. An actively feeding central black hole bathes its galaxy in radiation. It heats and disrupts the gas clouds from which new stars form. It sculpts the galaxy around it, sometimes suppressing the conditions that might allow planets like Earth to develop in relative peace. Our black hole's quietness is not unrelated to our existence. The calm at the center of our galaxy may be part of why the outer regions, where we live on a small planet circling an ordinary star, were able to settle and cool, and eventually wake up and begin to wonder. The silence at the heart of the Milky Way may have been a condition for the noise we make here so far from the center. Everything in the universe that has mass also rotates. Planets spin, stars spin, galaxies spin, and black holes spin too in some cases, with a velocity that approaches the ultimate speed limit of the universe. When a star collapses to form a black hole, it carries its rotation with it. And just as a spinning ice skater pulls their arms inward and accelerates, the collapsing star concentrates its angular momentum into a far smaller space. The result is a black hole that spins extraordinarily fast. The spin of a black hole is measured on a scale from 0 to 1, where 1 represents the theoretical maximum, the fastest a black hole can rotate without violating the laws of physics. Several black holes have been measured at spin values of 0.9 or higher, meaning their outer edges rotate at close to the speed of light. At those speeds, the geometry of space around the black hole is no longer symmetric. The spinning mass drags space-time around with it, in a way that stationary black holes do not. Even empty space, far from the event horizon, is set into rotation. This has consequences. Orbits near a rapidly spinning black hole precess and tilt in ways that orbits near a non-spinning object do not. The shadow cast by a spinning black hole is subtly different in shape from the shadow of one that is still. Spin leaves a mark on everything around it, even on nothing, even on space itself. There is an image that helps. Take a jar of honey, slow, golden, patient. Now lower a spoon into the center and begin to stir. The honey near the spoon moves first, dragged along by the turning. Further out, the honey resists, but still shifts slowly, pulled by what is happening at the center. Now imagine that the honey is space, and the spoon is a black hole spinning. This is called frame dragging, or more formally, the lens-thirring effect. A rotating mass pulls the fabric of space-time around with it as it turns. Not just matter, not just light, but space itself is set into a slow rotation around the spinning body. Near a black hole, this effect is dramatic. There exists a region outside the event horizon called the ergosphere, where frame dragging becomes so intense that nothing, not even light, can remain stationary relative to the distant stars. Everything in the ergosphere is forced to rotate in the same direction as the black hole, regardless of any other force acting on it. There is no anchor, no way to hold still. The rotation of space itself carries everything along. And remarkably, objects entering the ergosphere can, under the right conditions, extract energy from the black hole's spin. This is called the Penrose process, and it is one of the ways physicists believe the universe's most powerful jets of plasma are launched from near-spinning black holes. Energy pulled from the rotation of space itself. This pulling of space around a spinning mass is not only something that happens near black holes. It happens here, near Earth, right now. Our planet is not a black hole, its gravity is gentle, its rotation modest. But it spins, and in spinning it too drags the space-time around it into a slight rotation. The effect is vanishingly small compared to what a black hole produces, but it is real, and it has been measured. In 2011, a NASA mission called Gravity Probe B completed a years-long experiment. The probe carried 4 of the most nearly perfect spheres ever manufactured by human hands, gyroscopes so smooth and round that their surface deviated from a perfect sphere by no more than 40 atoms. These gyroscopes were pointed at a distant guide star and monitored for drift. After years of data collection and months of careful analysis, the team confirmed it. Earth's rotation causes a tiny, measurable twist in the space-time around it, exactly the amount general relativity predicted. The frame-dragging effect of our own spinning planet was real and detectable. Right now, as you lie still or sit quietly, the Earth's rotation is gently pulling the space-time around you in a slow, imperceptible twist. You are inside the frame-dragging field of your own planet. The same physics that shapes space around a billion solar mass black hole is present here in the room where you rest. quieter, almost immeasurably so. But present. You are already part of this. Not metaphorically, not as a poetic flourish. The gravity of the Earth curves the space-time you move through. The spin of the Earth frame drags the space around you. The mass of the Sun bends your path through the galaxy. The mass of the galaxy bends your path through the universe. You are embedded in a web of curved space-time, shaped by every massive object within gravitational reach, which is to say, every massive object that exists however distantly, because gravity has no edge, no wall where it simply stops. It diminishes with distance, but it never reaches zero. Every black hole in the observable universe exerts a gravitational influence on you so small as to be unmeasurable, but mathematically present. The supermassive black hole at the center of the Andromeda Galaxy, 2.5 million light-years away, is pulling on you right now, gently as you breathe. Physicists call this the principle of superposition, the idea that gravitational influences simply add together, each one present, regardless of the others. You are not separate from the universe observing it from the outside. You are woven into it. Your mass curves space too, a tiny amount, far too small to measure but real. You have a gravitational field. You are in the most precise physical sense part of the fabric. The universe is not something that happens elsewhere. It includes exactly where you are. Something warm is leaving every black hole in the universe. Not a flood, not a stream. Something closer to a whisper. A faint, steady seeping of energy so gentle that no instrument ever built has come close to detecting it directly. But the mathematics that describes it is among the most trusted in all of theoretical physics, sitting at the precise intersection of quantum mechanics and general relativity, two frameworks that otherwise refuse to cooperate. In 1974, Stephen Hawking combined those two frameworks and arrived at something unexpected. Empty space, he found, is not truly empty. At the quantum level, pairs of particles are constantly flickering into existence and annihilating each other, borrowing energy from the vacuum for the briefest possible moment before returning it. This happens everywhere, always. In the space around you right now. Near the event horizon of a black hole, something different can occur. One particle of such a pair falls inward past the horizon. The other escapes outward into space. The black hole, to conserve energy, loses a small amount of its mass. Over time, vast, patient, almost incomprehensible stretches of time, this process causes the black hole to slowly lose mass, to shrink, to fade. This is called Hawking radiation. It is so faint for any black hole of stellar mass or larger that the radiation is far colder than even the coldest reaches of deep space. Detecting it directly may never be possible with any technology we can presently imagine. But the warmth is there, leaving quietly. Every black hole is in its own imperceptible way letting go. Some truths live entirely in the mathematics patient and certain waiting for the instruments to catch up. Hawking radiation is one of them. Its existence is accepted by the overwhelming majority of theoretical physicists, not because it has been directly observed, it has not, but because the reasoning that produces it is so carefully constructed, so consistent with everything else. We know that doubting it would require doubting much of what underpins modern physics. The temperature of the radiation a black hole emits is inversely proportional to its mass. A smaller black hole is hotter, a larger black hole is colder. For a black hole with the mass of the Sun, the Hawking temperature is so extraordinarily low, a fraction of a degree above absolute zero, that it is billions of times colder than the cosmic microwave background radiation that fills all of space. In other words, a stellar mass black hole is actually absorbing more energy from the ambient warmth of the universe than it is emitting through Hawking radiation. It is for now growing slightly, not shrinking. Only when the universe cools further, in the unimaginably distant future, as the last stars burn out and the background radiation fades, will these black holes begin to lose mass faster than they gain it. Mathematics has looked far ahead, past the death of stars, past the cooling of galaxies, and described what will happen then. We simply have to trust the equations and wait. Given enough time, a black hole will vanish. Not with a collision, not with an explosion that announces itself across the galaxy. Something quieter, a long, slow, diminishing, stretched across a duration so vast that describing it in years becomes almost meaningless. A black hole with the mass of the Sun would take a length of time so vast it resists any familiar comparison. Written out in years, that number would require 67 zeros. The current age of the universe needs only 10. The evaporation timescale has 67. As the black hole shrinks, it heats. A smaller black hole emits more energetic Hawking radiation. So the process accelerates toward the end, the final moments of evaporation, releasing a brief, bright burst of energy as the last of the mass converts to radiation and the black hole ceases to exist. What remains after that moment? Nothing detectable. No mass, no gravity, no event horizon. The long curve of space-time that once bent around the black hole straightens slowly, like a surface returning to stillness after a stone has been removed. Space reorganizing itself around an absence. And somewhere in the universe, another black hole continues its own slow, diminishing, unhurried on its own timeline, moving toward the same quiet ending, billions of years away from now, in a universe that will look nothing like the one we inhabit tonight. The patience required to imagine these timescales is its own kind of meditation. Consider the largest black holes known, those ultramassive objects at the centers of the great galaxies, with masses of tens of billions of solar masses. Their evaporation timescales make the stellar mass estimate seem brief by comparison. A black hole of 1 billion solar masses would take roughly 10 to the power of 83 years to evaporate. A number with 83 zeros. A number for which there is no familiar analogy, no human-scale image that quite reaches it. The universe, as best we understand it, is roughly 13.8 billion years old. The evaporation of the largest black holes will occur at a time so far in the future that the ratio between now and then is similar to the ratio between the width of a single atom and the distance across the observable universe. And yet the process is already underway, has been since each black hole formed. The Hawking radiation leaving them right now is real, undetectable, vanishingly faint but present. Every black hole is already on its way to becoming nothing. It is simply taking the longest possible route. There is something almost restful in that the knowledge that even the most permanent-seeming things in the universe are participating in the same slow arc of change that touches everything else. Nothing is frozen. Nothing is permanent. Even the darkness moves eventually towards something lighter. But here is where the stillness meets a question that has no answer yet. When a black hole forms, it swallows things. Stars, gas, light. The history of everything that has ever fallen in the specific arrangement of atoms, the patterns, the information that defined each thing as what it was rather than something else. Quantum mechanics holds a deep principle. Information is never truly destroyed. The details of any physical system can always, in theory, be recovered from the way the system evolves. Nothing is ever erased from the universe's accounting, only scrambled, redistributed, made harder to read. But what happens to the information swallowed by a black hole? If Hawking radiation is truly random, truly thermal carrying, no encoded record of what fell in, then when the black hole finally evaporates, that information is gone, destroyed. The universe's accounting has a hole in it. This is the information paradox, and it sits at the center of theoretical physics, like a splinter that cannot be removed. Hawking himself spent decades wrestling with it, changing his position more than once. Others have proposed that information is somehow encoded in the Hawking radiation in subtle, complex ways. Some suggest it leaks out, gradually encrypted in correlations too faint to read. Others propose more radical solutions. No consensus has been reached. The universe swallows things, and whether it remembers them is a question we cannot yet answer. There are questions in physics that feel technical matters of calculation, of data, of instruments and numbers. And then there are questions that feel like they are about something else entirely, something larger than any particular equation. The information paradox is one of those. At its heart, it is asking whether the universe is fundamentally reversible, whether the past in principle is always recoverable from the present, whether the universe keeps a complete record of everything that has ever happened within it, or whether some events are genuinely permanently erased. If information can be destroyed, then the universe is not fully self-consistent. The past and the future are not symmetric in the way our deepest theories suggest they should be. Something fundamental about the nature of time and causality would need to be revised. If information cannot be destroyed, then our understanding of black holes, of Hawking radiation, or of quantum mechanics itself must be incomplete in some way we have not yet identified. Either answer requires us to give up something we currently believe. Physicists call this kind of situation a paradox, not because there is no answer, but because every available answer is uncomfortable. Every resolution requires a price. This is not a sign that the science is broken. It is a sign that it is alive, that it has found its way to an edge, to the place where the comfortable frameworks meet their limits, and the next understanding waits just beyond the reach of what we currently know how to do. Space is silent. There is no medium through which sound can travel in the vast emptiness between stars. No air to carry a wave, no surface to vibrate, no pathway for the pressure changes that make music possible to human ears. A black hole, in this sense, is perfectly, completely, and permanently silent. And yet, in the Perseus galaxy cluster, roughly 240 million light-years away, there is a black hole that produces something remarkable. It drives pressure waves through the hot gas that fills the space between galaxies, in the cluster waves of compression and rarefaction, rippling outward through the medium, like sound waves move through air. They are not sound in the technical sense. They cannot be heard, but they carry the same mathematical structure as sound waves, and NASA scientists taking those pressure waves and shifting them upward in frequency by a factor of enormous magnitude translated them into something that speakers could produce and human ears could register. What emerged was low and slow and resonant, not noise, something more deliberate than noise, a tone. Scientists still debate exactly how to characterize it and whether the word singing is technically appropriate. But there is a quality to the translated signal, a sustained rhythmic pressure from the heart of that galaxy cluster that resists more clinical descriptions. The universe, in its own frequency, in its own vast timescale, does something that rhymes with music. We simply needed to translate it far enough to hear. That translated tone has a name, or at least a position in the musical scale. The pressure waves from the black hole at the center of the Perseus cluster correspond, when shifted into human hearing range, to a note of approximately B-flat. Not the B-flat that a clarinet plays, not the B-flat that a choir holds at the end of a phrase. Something unimaginably lower, 57 octaves below the middle of a standard piano keyboard. Every octave represents a doubling of frequency. 57 octaves below middle C means the frequency is reduced by a factor of 2 57 times over. The resulting note would have a period, the time between one wave and the next, of roughly 10 million years. 10 million years between one wave and the next. The note has been sounding at that rate for billions of years. It was playing long before the Earth formed. It was playing when the first single-celled life appeared in the ancient oceans. It is still playing now. No human ear can hear it. No instrument built for music can register it. But it is there in the data, in the pressure maps of a galaxy cluster, in the mathematics of a wave moving through hot intergalactic gas. Something is resonating in the dark, at a frequency the universe chose long before anyone was listening. And now, for the first time in the history of that sound, something is. That note from the Perseus cluster is not the only rhythm black holes keep. When a black hole is actively spinning and surrounded by infalling material, it can produce quasi-periodic oscillations, regular fluctuations in the brightness of the light it emits, repeating like a heartbeat. These oscillations carry information about the geometry of space very close to the event horizon. In a region where gravity is most intense and the predictions of general relativity are most extreme. By studying these rhythms, physicists can measure the spin of a black hole, the size of its innermost stable orbit, and the behavior of matter in conditions that cannot be replicated in any laboratory on Earth. The rhythm of a black hole is a diagnostic tool. It tells the story of the space around it, the way a pulse tells a doctor something about the body producing it. Some black holes pulse in X-rays. Others vary in radio waves. Some flicker across multiple wavelengths simultaneously, like a complex drumbeat carrying several rhythms at once. Sagittarius A star, our own galaxy's central black hole, produces occasional flares, brief brightenings that last minutes to hours, caused by small amounts of material being heated and disrupted near the innermost orbit. A flicker, a brief brightening, and then quiet again. The heart of our galaxy has a pulse, irregular, slow, mostly still, but present. A rhythm that has been beating since long before there was anyone near enough to notice. Some researchers have carried this idea further, not just that black holes produce rhythms, but that those rhythms may have shaped the universe itself. In the very early universe, in the first fractions of a second after the beginning, conditions were so extreme that density fluctuations, tiny variations in how much matter was packed into different regions of space, determined where galaxies would eventually form. Regions that were slightly denser, attracted more matter, grew more massive, and eventually became the large structures we see today. Some physicists have proposed that primordial black holes, if they formed in those early moments, would have contributed to those density fluctuations, that the seeds of galaxy formation were partly set by the presence of these ancient, extremely early objects. The pattern of galaxies we observe tonight, the great walls and filaments of galaxy clusters, the vast, empty voids between them, may carry within it the imprint of processes that happened in the first second of existence. The structure of everything visible may be in part a record of what happened before the first stars lit. We do not know this for certain. The evidence is suggestive, not conclusive. But the possibility sits quietly in the data, waiting for instruments sensitive enough to either confirm it or set it aside. Somewhere in the arrangement of galaxies above you tonight, there may be an echo, faint, ancient, written in the language of position and density, of something that happened at the very beginning of everything. When two black holes find each other, the universe pays attention. They approach slowly at first, two massive objects caught in each other's gravity, orbiting one another across distances that shrink over millions of years. As they spiral closer, they move faster. The orbit tightens. The energy they carry must go somewhere, and it goes into space itself, rippling outward as gravitational waves carrying the record of the inspiral across the universe. In the final moments before merger, the two black holes are moving at a significant fraction of the speed of light, orbiting each other dozens of times per second. The gravitational waves they produce in those last seconds are the most energetic events in the known universe. At the moment of merger, the energy released as gravitational waves exceeds, for a brief instant, the combined light output of every star in the observable universe. Not the light of one star, not one galaxy. Every star, every galaxy. Every photon streaming from every burning nuclear furnace across the entire observable cosmos, surpassed in that fraction of a second by the energy of two black holes becoming one, and none of it arrives as light. None of it would warm your face or illuminate a room. It passes through everything, through planets, through stars, through you as a whisper in the geometry of space, a momentary stretching and squeezing of distance itself. The most powerful event in the universe, And it is invisible, silent, and gentle enough to pass through your body without your knowledge. What carries the news of that collision is stranger than light. Light is a wave in electromagnetic fields. It needs those fields to exist, and it travels through space, affected by the matter and energy it encounters. Gravitational waves are different. They are not waves moving through space. They are waves of space itself, oscillations in the fabric of space-time, rippling outward from the merger at the speed of light, passing through everything without being absorbed or scattered. A gravitational wave arriving at Earth does not interact with the planet the way light does. It does not heat the surface or ionize the atmosphere. It simply passes through stretching space very slightly in one direction, while compressing it in the perpendicular direction, then reversing like a slow breath the universe takes without lungs. The stretching and compressing affects everything the wave passes through, including you, including this room, including the distance between your eyes and the wall across from you. But the effect is so extraordinarily small, a fraction of the width of a proton for the strongest waves that have reached us, that it is completely imperceptible to any human sense. It was imperceptible to instruments too for most of human history. That changed only when our technology became precise enough to measure a change in distance, smaller than anything previously thought measurable. And when that threshold was crossed, the universe immediately began sending signals. It had been sending them all along. We simply had not yet built the ears. On the 14th of September 2015, two black holes sent a message that had been traveling for more than 1 billion years. It arrived at a detector in Louisiana first, then at a second detector in Washington state 7 milliseconds later, traveling at the speed of light. Each detector is an instrument called a laser interferometer, 2 tunnels each, 4 kilometers long, arranged in an L shape, with laser beams bouncing between mirrors at each end. When the gravitational wave passed, it stretched one arm of the L by an almost incomprehensible amount, roughly 1,000th the diameter of a proton, while simultaneously compressing the other. The lasers sensitive to that change registered a signal. The signal lasted less than 0.2 of a second. A brief chirp rising in frequency, then silent. In that chirp was encoded everything about the collision, the masses of the two black holes, their distance, their final spin. Physicists could read the signal like a score and reconstruct the merger that produced it. Two black holes found each other across the dark, and in their final moment, became one. The mass that disappeared in that, joining enough to outweigh 600,000 Earths, was converted entirely to gravitational wave energy in under a second. We felt it. That signal had been traveling since before complex life existed on Earth. When those two black holes merged, more than 1 billion years ago, in a galaxy far beyond our own, the most complex things alive on this planet were simple multicellular organisms, drifting in shallow ancient seas. There were no eyes to see, no ears to hear, no minds to wonder. The gravitational wave left the site of the merger and began its journey. It passed through the space between galaxies, undisturbed by the matter and energy it encountered, carrying its precise record of the collision at the speed of light. While it traveled, evolution continued on Earth. Fish appeared, then forests, then dinosaurs rose and fell. Mammals diversified. Primates descended from trees. One lineage of those primates began to walk upright, then to use tools, then to speak, then to write, then to build telescopes and lasers and instruments of extraordinary precision. And then at almost exactly the moment when the instruments became sensitive enough to detect a gravitational wave, the wave arrived. This could be coincidence. Probably it is. The universe does not arrange arrivals for audiences. And yet there is something in that timing that resists being dismissed entirely, the sense that curiosity and cosmos arrived at the same threshold, at the same moment, and the universe sent its oldest stored message just as we finally learned how to open it. The instruments that caught that signal belonged to a collaboration called LIGO, the Laser Interferometer Gravitational Wave Observatory, and they represent one of the most precise measurement achievements in the history of human science. To understand what they measure, consider this. The 4-kilometer arms of each detector must be monitored for length changes smaller than 1/10,000th the diameter of a proton. A proton is itself roughly 100,000 times smaller than an atom. An atom is already far too small to see with any optical microscope, and yet the change must be measured to 1/10,000th of even that. To achieve this, the mirrors at the ends of the arms are among the most perfectly polished surfaces ever made. The laser light bouncing between them is stabilized to extraordinary precision. The entire system is isolated from vibrations, from traffic, from ocean waves, from the footsteps of researchers in the building, through layers of carefully engineered suspension systems. Even so, the detectors are so sensitive that a truck passing on a road kilometers away can produce a signal. Earthquakes anywhere on Earth are visible in the data. So are the footsteps of someone walking nearby. The data is full of noise. Finding a gravitational wave signal within it requires algorithms of great sophistication, comparing signals across two detectors separated by thousands of kilometers to distinguish a real cosmic event from local disturbance. The universe whispers, and we built an instrument delicate enough to hear it just barely just now, after centuries of preparation. After two black holes collide and merge, the new single black hole they form is not immediately at rest. The merger is violent in its geometry, two spinning massive objects arriving from different angles carrying different amounts of angular momentum. The resulting object is distorted, asymmetric, oscillating. It rings. The technical term is ring down, and it describes the process by which the newly merged black hole settles into its final state. Like a bell struck by a hammer, the black hole vibrates, emitting gravitational waves. As it does, each oscillation slightly smaller than the last, until the distortions damp away and the black hole settles into the smooth, symmetric shape that general relativity prescribes. The frequency and decay rate of those ring-down oscillations are predicted precisely by general relativity. They depend on only two things: the mass and the spin of the final black hole. Measure the ring-down signal, and you can determine both. This has now been done for multiple detected mergers, and in each case, the ring-down matches the predictions to within measurement precision. A bell ringing in space, cooling into stillness, confirming by its song that the equations written more than a century ago remain correct at the most extreme conditions the universe produces. The physics holds. The bell rings, and then the silence returns deeper than before, because now there is one massive still object where two spinning, spiraling ones used to be. Stillness arrived. But it had to ring first. From the darkness of a black hole, something bright is launched. In some active black hole systems, particularly those surrounded by rich accretion disks and threaded by powerful magnetic fields, narrow beams of plasma are accelerated outward from the poles at velocities approaching the speed of light. These are called relativistic jets, and they are among the most dramatic structures in the known universe. The mechanism that produces them is not fully understood. It remains one of the active areas of research in high-energy astrophysics. The leading explanation involves the magnetic field lines that thread through the accretion disk, twisted and wound by the rotation of the black hole and the orbiting material, until they form a kind of magnetic nozzle that funnels plasma outward along the rotation axis. The black hole itself may contribute directly through the Blandford-Znajek process, a mechanism by which energy is extracted from the spin of the black hole via magnetic fields and channeled into the jet. The plasma in these jets moves so fast that, due to special relativity, jets pointed nearly toward Earth can appear to move faster than light, an optical illusion produced by the geometry of the motion, not a violation of any physical law. They are not breaking the rules of the universe. They are simply moving fast enough that the light they emit catches up with itself in a way that looks from our angle like something impossible. appearance and reality once again gently diverging. These jets do not stay close to home. Launched from a region no larger than a solar system, they travel outward into the surrounding galaxy and beyond, carrying energy and magnetized plasma across distances that dwarf anything else in the universe produced by a single object. Some jets have been measured extending for millions of light years. In one remarkable case, the jet from a galaxy called Hercules A stretches outward in both directions to a combined length of roughly 1.5 million light-years, more than half the distance between the Milky Way and the Andromeda galaxy. As the jet travels, it interacts with the gas it encounters. It heats the intergalactic medium. It pushes gas clouds outward, sometimes suppressing star formation across vast regions of the galaxy and beyond. In some cases, it can also compress gas clouds and trigger new star formation in regions the jet touches. The black hole at the center is not passive. Through its jets, it reaches out across scales that no other single object can match. It shapes the temperature and density of gas millions of light-years away. It influences whether new stars will be born in regions it has never directly touched. In this way, a black hole at the center of one galaxy can influence the evolution of another. Gravity holds things together at close range. Jets carry influence across distances that gravity alone could never bridge so effectively. The reach of a black hole is far greater than its darkness suggests. Not everything that falls toward a black hole is lost. The accretion disk surrounding an actively feeding black hole is a turbulent, magnetically complex environment. Material spirals inward along the disk, losing energy and angular momentum to friction and magnetic interactions. Some of that material crosses the event horizon, but some of it, perhaps as much as half in some systems, is flung outward before it ever reaches the point of no return. These outflows, called winds, carry material away from the black hole at speeds of thousands of kilometers per second. They are enriched with heavy elements, carbon, oxygen, iron, and others, produced in the nuclear furnaces of stars that were consumed and processed through the extreme environment of the accretion disk. Those enriched winds travel outward into the galaxy, mixing with the surrounding interstellar gas. They contribute to the chemical evolution of the galaxy, adding elements that will later be incorporated into new molecular clouds, new stars, new planetary systems. Some of the atoms in your body, carbon, oxygen, the iron in your blood, may have passed through the accretion disk of a black hole at some point in the long history of the matter that eventually became you, processed by the most extreme environment, short of the singularity itself, then scattered back into the galaxy to begin a long journey through generations of stars and clouds before arriving, eventually here. You are in part material that a black hole chose not to keep. This changes something about how a black hole feels once you hold it long enough. The easy image is of pure consumption, a darkness that takes and does not give, that swallows and does not return. And it is true that what crosses the event horizon does not come back. That part of the picture is accurate. But the fuller picture includes the winds and the jets and the enriched outflows and the heating of intergalactic gas and the triggering of new star formation in distant clouds. It includes the pressure waves moving through the Perseus cluster, that slow, deep rhythm which actually prevent the gas in the cluster from cooling and collapsing too fast, regulating the pace at which new stars are born. Black holes in their active phases do not simply consume their environments. They regulate them. They heat them, enrich them, sculpt them. They distribute the products of stellar death across vast distances. They set the rhythm of star formation across entire galaxy clusters. Destruction and creation operating from the same object at the same time through the same processes. The accretion disk, the jets, the winds, these are not side effects of a black hole's hunger. They are the black hole in conversation with its galaxy. A long, slow, immensely energetic dialogue between the center and the whole. And what the center gives back, scattered outward across millions of light years, becomes the raw material of everything that comes next. At the center of every black hole, the equations arrive at a wall. Not a physical wall, a mathematical one. General relativity, the framework that describes gravity with such precision everywhere else, follows the infalling material all the way to the center, and there produces an answer that cannot be physical: infinite density, infinite curvature, a point where the mathematics simply stops making sense. This point is called a singularity, and physicists are nearly unanimous that it is not a real description of what actually exists there. It is instead a signal, the way a theory announces its own limits. The way a map at its edge writes the words "beyond here we do not know." A singularity in an equation is not a discovery about the universe. It is a discovery about the theory producing it. It means the theory has been pushed past the conditions for which it was designed. The answer it gives is not wrong exactly. It is the correct output of an incomplete framework applied where a more complete one is needed. General relativity is a theory of the very large of gravity at cosmic scales. Quantum mechanics is a theory of the very small of particles, probabilities, and the granular nature of energy. At the singularity, both matter. The object is both unimaginably small and unimaginably massive. Both theories must apply simultaneously, and they do not agree. Not yet. The singularity is not where the universe breaks down. It is where our understanding of it does. Something is happening there. We simply do not yet have the language to say what. The search for that language has occupied some of the finest scientific minds of the last century, and it continues today, patient, incremental, and still unfinished. What is needed is a theory of quantum gravity, a framework that describes what happens when both quantum effects and gravitational effects are important simultaneously. Such a theory would replace both general relativity and quantum mechanics in the extreme regimes where they conflict, reducing to each in the limits where that theory already works well. Several serious candidates exist. String theory proposes that the fundamental constituents of nature are not point particles, but tiny vibrating strings whose different vibrational modes produce the different particles we observe. Loop quantum gravity proposes that space-time itself is quantized, made of discrete chunks like pixels, rather than a smooth continuum. Other approaches exist too, some more speculative, some more mathematical. None has yet produced a prediction that could be tested with current instruments and clearly distinguished from the predictions of existing theories. None has been confirmed or ruled out by experiment. This is not unusual for physics at its frontier. General relativity itself was proposed decades before many of its predictions were testable. The mathematics often arrives before the instruments. What is unusual is the depth of the disagreement between the frameworks that need to be unified. General relativity and quantum mechanics are not slightly different, they are built on different assumptions about the nature of reality itself, and reconciling those assumptions has proven to be among the most difficult intellectual challenges in the history of science. The answer is somewhere. We simply have not found the right question yet. Before the name black hole existed, before the mathematics was fully understood, there was a simpler and perhaps more poetic description. In the middle decades of the 20th century, before John Wheeler coined the term black hole in 1967, collapsed, stellar remnants of extreme density were sometimes called frozen stars. The name came from the outside view, from what a distant observer would see as an object collapse toward the Schwarzschild radius, the critical boundary that would later be called the event horizon. From outside, the collapsing star would appear to slow, to redden, to dim, its surface light stretched and weakened as gravity grew more intense. It would appear to freeze at the threshold, its final moment stretched across time, never quite completing the collapse. Frozen, at the edge, forever. It is an image that general relativity genuinely supports. From outside, the star never appears to cross its own event horizon. It hangs there in a kind of eternal pause, its last light reddening toward invisibility. From the perspective of the collapsing material, no such pause occurs. The collapse continues through the horizon inward, but that perspective can never be communicated back to the outside universe. So Frozen Star was not wrong. It was simply the view from one side of a boundary that allows only one-way communication. The universe occasionally keeps two true descriptions of the same event, one for each side of a line that cannot be crossed in both directions. The speed of collapse from inside the falling material is almost beyond imagining. A massive star, one with perhaps 20 or 30 times the mass of the Sun, lives its life, burning hydrogen, then helium, then heavier elements in its core, each stage shorter than the last. When it reaches iron, the burning stops. Iron does not release energy through fusion. It absorbs it. The core, no longer supported by the outward pressure of nuclear burning, begins to collapse. What happens next takes less time than it takes to read this sentence. The iron core, roughly the mass of the Sun, compressed into a sphere the size of Earth, collapses to the size of a city in a fraction of a second. The infalling outer layers hit the suddenly rigid inner core and rebound in a shockwave. That shockwave, amplified by an enormous flood of neutrinos pouring out of the newly formed neutron star or black hole at the center, blows the outer layers of the star outward. This is a supernova, one of the brightest events in the universe, briefly outshining the entire galaxy containing it. And at the center, if the core was massive enough, even the neutron star phase is skipped. The collapse continues past neutron star density, past any known form of stable matter, into the black hole state in less time than a human breath. The most dramatic transformation in stellar physics happens faster than a blink in a core no larger than a city, under conditions no laboratory could replicate. And then the light rises and the darkness remains. What remains after the light fades is defined only by what cannot be seen. A newly formed black hole carries no label, no marker, no visible surface. The space where the star once burned is simply empty, except that it is not quite empty, because the gravity is still there, undiminished, shaping the paths of anything that comes near. Nearby gas clouds feel the pull and begin to drift closer. A companion star, if one orbits nearby, may begin to shed material that spirals toward the black hole, forming an accretion disk and producing X-rays that can be detected from Earth. This is in fact how many stellar mass black holes have been discovered, not by seeing them directly but by watching the behavior of material near them. A black hole reveals itself through its effects on everything around it, never through itself. There is a quality of patience in that the way something can be known entirely through its influence, through what it does to the space it occupies, without ever showing a face. Some of the most important things in the world work this way. Gravity itself was understood for centuries before anyone had a physical picture of why it existed. The nucleus of an atom was inferred from the way particles scattered off it, long before it was directly imaged. Dark matter is known today only through its gravitational effects on visible matter. The universe contains many things that announce themselves only through what surrounds them. The black hole is simply the most extreme example of this deeply common pattern. Presence felt entirely through effect. There is a moment in the life of every massive star when the balance tips. For millions of years, the star maintains an equilibrium, the outward pressure of nuclear burning pushing against the inward pull of its own gravity. Neither wins. The star holds its shape, its warmth, its light. Then the fuel runs out. The collapse that follows from the star's own perspective takes less than a second for the core. But the shockwave generated by that collapse takes hours to reach the outer surface. During those hours, the star's surface has no knowledge of what has happened at its center. It continues to shine unaware. Then the shockwave arrives. The outer layers of the star are ejected at tens of thousands of kilometers per second, carrying with them all the heavy elements synthesized over the star's lifetime: carbon, oxygen, neon, magnesium, silicon, sulfur, calcium, iron scattered outward into the surrounding space. These elements were not present at the beginning of the universe. The early cosmos contained mostly hydrogen and helium. Every heavier element in existence was made inside a star and released by its death. The calcium in your bones was forged in the core of a star that died before the sun was born. The iron in your blood came from a supernova that may have occurred billions of years ago in a galaxy that no longer looks as it did then. You are assembled from the deaths of stars. The black hole that sometimes follows that death is made of the same history. You and the black hole share an origin. For a brief time, hours to weeks depending on its mass, a supernova can be the brightest single object in the observable universe. The light it pours out during that period can exceed the combined output of the entire galaxy surrounding it. Ancient astronomers observing supernovae in nearby galaxies, before any of the physics was understood, recorded stars that appeared suddenly in the sky, where none had been before, shone brilliantly for weeks or months, then slowly faded. In 1054, observers in China and the Arab world recorded a new star so bright it was visible in daylight for nearly a month. What remained of that explosion is the Crab Nebula, a still expanding cloud of luminous gas, roughly 11 light-years across, centered on a rapidly spinning neutron star called a pulsar that pulses 30 times per second. Nearly 1,000 years later, that remnant is still glowing, still expanding, still carrying the energy of a moment that lasted seconds. And at the center of it, the collapsed core of the star, spinning and magnetic beaming radiation outward with every rotation, is a record of the instant of collapse preserved in a dense spinning remnant detectable from Earth by the regularity of its pulse. The universe keeps records in different ways. Light, gravity, spin pressure, waves, the chemical composition of nebulae. The supernova of 1054 left records in all of these. Ancient light and ancient spin still teaching nearly a millennium later. After the light of a supernova fades, after the nebula begins its long expansion into the surrounding space, the black hole remains. No glow of its own, no expanding shell to mark its presence, no pulse of radiation from its surface because it has no surface. Simply a region of space where the gravity curves inward so steeply that the ordinary landmarks of physics no longer apply. From outside, the black hole is defined by its silence. It does not emit. It does not announce. It waits with what can only be called patience, a word that applies to it not because it has intentions but because it persists. It was there before the nebula had expanded far. It will still be there after the nebula has dispersed entirely back into the interstellar medium, which will take perhaps 100,000 years. The nebula is brilliant, complex, changing, beautiful. The black hole is none of those things from outside. And yet the black hole will outlast the nebula by an almost incomprehensible margin. The nebula will dissolve into the surrounding gas. The black hole will remain dark and still for trillions of years longer than the current age of the universe, by a factor that no familiar number can bridge. Silence sometimes outlasts everything that makes noise. The patient thing, the invisible thing, the thing that simply holds its gravity and waits, sometimes that is the thing that lasts. There may be black holes that did not wait for any star to die. In the first fractions of a second, after the beginning of the universe, conditions were unlike anything that exists today. The temperature was so extreme, the density so vast, that tiny fluctuations in the distribution of matter regions that were very slightly denser than their surroundings could collapse directly into black holes without any star as an intermediary step. These are called primordial black holes, and their existence remains hypothetical. No primordial black hole has been confirmed directly, but the conditions that would have produced them were real, and the mathematics that describes their possible formation is consistent with everything else we know about the early universe. If they formed, they could range enormously in mass, from objects smaller than an asteroid to objects far more massive than any star. The very small ones, if they formed, would have already evaporated through Hawking radiation long ago. The larger ones would still be present, drifting through the universe today, dark and largely invisible. Their existence would leave subtle imprints in the way light from distant sources is occasionally bent in the distribution of mass in the early universe, in the gravitational wave signals produced if they merge. Searches for these signatures are ongoing. The data does not yet clearly confirm or rule out primordial black holes as a significant population. But somewhere in the universe there may be black holes older than any star witnesses to the first second of everything, still here, still waiting, older than anything else that exists. Primordial black holes, if they exist in sufficient numbers, may be part of the answer to one of cosmology's deepest puzzles. Most of the matter in the universe is invisible. Not dim, not faint, not difficult to detect. Genuinely invisible to every form of electromagnetic radiation we have ever used to observe the universe. It does not emit light. It does not absorb light. It does not interact with ordinary matter, except through gravity. It is called dark matter, and it makes up roughly 85% of all the matter in the universe. The atoms, molecules, stars, planets, and people that make up everything we have ever directly observed constitute only about 15% of the matter that exists. What the other 85% consists of is unknown. Primordial black holes are one candidate. If they formed in large enough numbers during the early universe, and if their mass distribution falls within certain ranges, they could account for some or all of the dark matter we infer from galactic rotation curves and the large-scale structure of the cosmos. Current observations constrain but do not eliminate this possibility. Some mass ranges for primordial black holes are ruled out. They would have caused effects we would have already detected. But a window remains open, particularly for black holes, with masses in certain intermediate ranges. The dark matter that holds the Milky Way together, that shapes the orbits of stars across the galaxy, may be in part, or perhaps in whole, a vast ancient population of black holes, drifting invisibly through the dark since the first moments of time. The universe may be darker and older and stranger than the stars suggest. Two kinds of invisible things hold the universe together. Dark matter, whatever it is, pulls. It provides the extra gravity that keeps galaxies from flying apart, that bends light from distant sources in ways visible matter alone cannot explain, that scaffolds the large-scale structure of the cosmos into its vast web of filaments and voids. Black holes are also invisible, also known only through their gravity, also felt rather than seen, inferred rather than directly observed. The resemblance is not coincidence, it is a reflection of something deep about how the universe communicates its contents. The things that shape the largest structures tend to be the things that interact least with light. They do not shine, they do not scatter, they simply pull patiently across whatever distance separates them from everything else. There is a quiet lesson in that. The most influential things are not always the most visible ones. The structures that hold the largest systems together are often the ones that operate most silently, most consistently without announcement. A galaxy is held together mostly by what cannot be seen. Its visible stars, glowing and brilliant and beautiful, are a minority, a luminous tracery stretched across a much larger, darker framework that provides most of the gravitational scaffolding. The light is real. The stars are real. But they are, in a sense, the surface of something deeper, the visible portion of a mostly invisible architecture. Looking at a galaxy in an image, you are seeing perhaps 15% of what is actually there. The rest is holding it together quietly in the dark. Light, the fastest thing in the universe, can be stopped in its tracks. Not slowed, stopped. Redirected. Bent so completely that it travels in a circle, never escaping, never arriving anywhere. This is what a black hole does to light that passes close enough. The intense curvature of space-time near the event horizon bends the path of light the way a glass lens bends it, except that the bending agent is not glass, but the geometry of space itself, curved by mass to a degree no material object could produce. At a certain distance from a black hole called the photon sphere, the curvature of space-time is exactly sufficient to make light travel in a circular orbit. A photon, arriving at that distance, moving at exactly the right angle, will circle the black hole indefinitely, neither falling in nor escaping outward. That orbit is unstable, however. A tiny perturbation inward, and the photon spirals into the event horizon. A tiny perturbation outward, and it escapes to infinity. The photon sphere is a knife-edge balance, maintained only in theory, disrupted by any small disturbance. But the bending of light at distances beyond the photon sphere is real and dramatic, and it has a practical application: gravitational lensing. A massive black hole, acting as a lens, can magnify and distort the image of objects behind it, allowing astronomers to observe things that would otherwise be too faint or too distant to detect. The very darkness that makes black holes invisible in one sense makes them powerful magnifiers in another. They hide themselves and reveal everything behind them. Through that gravitational magnification, the universe has shown us things it would otherwise have kept hidden. By carefully studying the distorted images of distant galaxies behind massive black holes and galaxy clusters, astronomers have discovered objects at the farthest reaches of the observable universe, galaxies so ancient that their light left them when the cosmos was only a few 100 million years old, long before the Milky Way existed in its current form. Some of these distant galaxies contain their own active black holes blazing as quasars, and the lensing that magnifies them is produced by other black holes and dark matter halos far closer to us, acting as nature's telescopes, concentrating light that would otherwise be too faint to detect even with our most powerful instruments. In this way, the universe has constructed an optical system of its own layers of gravitational lenses, stacked across billions of light years, each bending and magnifying the light of what lies beyond, creating alignments that allow the near to illuminate the far. Astronomers have also used gravitational lensing to detect black holes that would otherwise leave no visible signature by the subtle distortion they produce in the images of background stars. A technique called microlensing. A star's image brightens and distorts as an unseen massive object passes between it and us, then returns to normal when the alignment shifts. A brief brightening, a gentle curve, and in that curve the shadow of a dark object that left no other trace. The first direct image of a black hole required the entire planet. For years before the image was released, the Event Horizon Telescope collaboration worked to coordinate radio telescope observatories spread across the globe, each collecting data simultaneously during a brief observation window when weather conditions at all sites needed to be favorable at once. The target was the black hole at the center of the galaxy, Messier 87, chosen because it is one of the largest black holes known in terms of its angular size, as seen from Earth, despite being 55 million light-years away. Event Horizon is wide enough that an Earth-sized telescope array could resolve its shadow. Each observatory recorded its data on specialized hard drives, synchronized to atomic clocks, accurate to a fraction of a nanosecond. Those drives were then shipped to processing centers at the MIT Haystack Observatory and the Max Planck Institute for Radio Astronomy, where algorithms developed over years combined the signals as if they had come from a single dish, as wide as the distance between the most widely separated telescopes. Antarctica to Spain, Hawaii to Chile, each baseline adding resolution, each additional telescope sharpening the image. The processing took months. The image that emerged showed the glowing ring of heated gas surrounding the dark central shadow, consistent with the predictions of general relativity for a black hole of 6.5 billion solar masses. Every continent except Australia participated. The image belonged to no single nation and no single institution. It was, in a quiet way, a portrait of the whole planet paying attention. What that image showed is stranger than a photograph of a distant object has any right to be. The bright ring surrounding the dark center is not simply the glow of the accretion disk as seen head-on. Because the black hole's gravity bends light so severely, photons from the far side of the accretion disk, the side facing away from us, are bent around the black hole and redirected toward our telescopes. This means the image contains light from regions of the disk that face in directions other than toward Earth. The top of the ring in the image of Messier 87's black hole is brighter than the bottom, not because one side glows more intensely, but because the black hole is rotating, and material on the side moving toward us is Doppler boosted. Its light blue shifted and brightened by the motion. The dark region at the center, the shadow, is not quite the event horizon itself. It is the silhouette cast by the event horizon's effect on light, the region from which no photons escape to reach us, bounded by the photon sphere. Its diameter is roughly 2.5 times the diameter of the event horizon. Every feature of that image is a consequence of curved space-time, behaving exactly as the equations predict, in conditions no human experiment could replicate. A theory written on paper in 1915, confirmed in a photograph assembled from hard drives shipped from Antarctica and Hawaii. What the mathematics promised, the image delivered. The shadow in that image has a name and a measured size that carries weight. The black hole shadow of Messier 87's central black hole, as observed by the Event Horizon Telescope, has an angular diameter consistent with the predictions of general relativity for a black hole of 6.5 billion solar masses with an uncertainty of roughly 7%. 6.5 billion solar masses. An object with an event horizon larger than our entire solar system, and yet visible to us only as a ring of orange light surrounding a dark circle observed in radio waves at a distance of 55 million light-years. The size of the shadow matches theory. Its shape is consistent with theory. The brightness asymmetry caused by the rotation of the black hole is consistent with theory. Each consistency is not just a measurement, it is the universe saying quietly that the equations written on paper in 1915 still hold here at the most extreme place we have ever looked. Einstein could not have known. The equations did. The shadow is, in this sense, not just an image of a black hole. It is an image of the reliability of mathematics, a portrait of the fact that the universe obeys rules and that patient, careful reasoning can discover what those rules are, and that they remain true in places where no human could ever go to. Check. The framework that predicted all of this was completed in November of 1915. Albert Einstein, working in Berlin, published the final form of the field equations of general relativity, 10 equations that describe how matter and energy curve space-time, and how that curved space-time directs the motion of matter, energy. He had been working toward them for roughly 10 years, through a period of intellectual struggle that he later described as the hardest of his life. The mathematics required was differential geometry, a branch of mathematics that had been developed decades earlier for entirely different purposes, and that Einstein had to learn as he worked. The final equations were right, not approximately right. Not right in the regime of weak gravity and slow speeds, right in every regime that has since been tested, including the extreme gravity of black holes, the expansion of the universe, the existence of gravitational waves, and the behavior of GPS satellites in Earth orbit. A single human mind working through a decade of difficulty arrived at equations that describe the universe at every scale, where gravity matters, from the falling of an apple to the merger of black holes a billion light-years away. Einstein himself doubted many of their implications. He introduced a correction term to prevent the equations from predicting an expanding universe, then later called it his greatest mistake when expansion was confirmed. He doubted that black holes could form. He doubted that gravitational waves carried real energy. The equations disagreed with him on all of these. The equations were right. The man who wrote those equations did not think the universe would take them quite so seriously. Einstein's doubts about black holes were not idle. He published a paper in 1939, arguing that rotating systems of stars could not collapse beyond a certain density, that nature would always find a way to halt the process before a Schwarzschild singularity formed. His argument was reasonable given what was known at the time. It was also wrong. The same year, Robert Oppenheimer and his student Hartland Snyder published a paper showing that a sufficiently massive non-rotating star of dust would indeed collapse completely, that general relativity applied consistently predicted the formation of what we now call a black hole, with no natural mechanism to prevent it. Einstein reportedly was not convinced. The paper was largely ignored during the war years that followed. It took another generation of physicists, including John Wheeler, who coined the term black hole, and Roger Penrose, who proved mathematically that singularities must form inside collapsed objects, to establish that black holes were not a mathematical curiosity, but a physical prediction that the universe was likely to have acted upon many times throughout its history. Einstein's equations knew before Einstein did, and now we have images, and gravitational wave detections, and orbital measurements of stars near Sagittarius A star. The universe confirmed what the mathematics said in its own time, on its own terms, without asking anyone's permission. Nature did not wait for consensus. While physicists debated whether black holes could truly form, the universe was making them in large numbers. Every massive star that exhausted its fuel and collapsed, every neutron star that accreted enough mass from a companion to tip past the stability limit, each became a black hole quietly, without announcement, consistent with the equations and indifferent to the debate. We now know that black holes are not rare. Stellar mass black holes in the Milky Way alone are estimated to number in the hundreds of millions. Every galaxy of significant size appears to harbor a supermassive black hole at its center. The universe is populated with black holes across a vast range of masses, from a few times the mass of the Sun to billions of solar masses. They are, in a sense, one of the universe's preferred outcomes for concentrated mass. Not exceptional, not rare, simply the natural conclusion of gravity, applied to sufficient density, operating across sufficient time. They are common, they are ancient, they are distributed across every corner of the observable universe. And yet for most of human history, no one knew they existed. Not because they were hiding, they were always there, always shaping the motion of stars, always bending light, always waiting, but because knowing requires instruments, and instruments require time, and time requires the slow accumulation of generations of curious people building on what came before. The black holes did not reveal themselves. We grew slowly, capable of finding them. The black hole at the center of our own galaxy kept its secret for a long time. Sagittarius A star sits behind a thick curtain of gas and dust that blocks visible light almost completely. For decades, astronomers knew something massive and unusual resided at the galactic center. The motion of nearby stars made that clear, but direct observation was impossible in the wavelengths most telescopes were designed to use. Radio waves and infrared light passed through the dust more freely. By the 1990s, two independent groups, one led by Reinhard Genzel in Germany and one led by Andrea Ghez in the United States, began using infrared telescopes equipped with adaptive optics systems to track the individual stars closest to the galactic center. Over years of patient observation, the orbits of those stars were mapped with increasing precision. The star called Stu was tracked through a complete orbit. From its motion, the mass of the central object could be calculated 4 million solar masses, concentrated within a volume so small that no known alternative to a black hole was physically plausible. In 2022, the Event Horizon Telescope released the first direct image of Sagittarius A star, a glowing ring of gas, similar in structure to the image of Messier 87's black hole, but much more difficult to obtain. because our own black hole is smaller and its brightness fluctuates more rapidly. The image took 5 years to process after the observations were made. 5 years of computation for a few seconds of clarity about something 26,000 light-years away. Patience in science, as in the universe, is not optional. Our galaxy's heart beats differently from most. Across the observable universe, astronomers have catalogued thousands of galaxies whose central black holes are in active blazing phases, consuming material at high rates, pouring radiation across enormous distances, shaping the evolution of everything around them through the sheer energy of what they release. The Milky Way is not among them. Sagittarius A star is, by the standards of active galactic nuclei, extraordinarily quiet. Its luminosity, the rate at which it currently releases energy, is roughly 10 billion times lower than what it would produce if it were feeding at the maximum rate its mass would allow. It is operating at a tiny fraction of its potential. This quietness is not permanent. Evidence suggests that roughly 3 to 4 million years ago, Sagittarius A star went through a period of significantly higher activity, bright enough to illuminate vast structures of gas above and below the plane of the galaxy now, called the Fermi bubbles, which extend roughly 25,000 light-years in each direction and are still glowing faintly in gamma rays today. We live in the afterglow of that outburst, long after the fire has dimmed. The Fermi bubbles are the scar tissue of an event none of our ancestors were present to witness. A brightening at the galactic center that would have made Sagittarius A star visible from Earth as a faint but steady glow even through the dust if any eyes had been there to look. Our galaxy carries its history written in light. We are simply reading it late. Farther away, where the universe was younger, the black holes did not rest. In the early universe, when the cosmos was perhaps 1 to 3 billion years old, a fraction of its current age, a significant fraction of large galaxies hosted actively feeding central black holes. These are the objects called quasars, quasi-stellar radio sources, first identified in the middle of the 20th century as point-like sources of light far brighter than any star, yet clearly extragalactic. The brightest quasars pour out energy equivalent to thousands of entire galaxies combined. They are visible across nearly the entire observable universe. Some of the most distant objects ever detected are quasars, their light having traveled for more than 13 billion years before reaching our telescopes. They were the dominant energy sources in the universe during what astronomers call the quasar epoch, a period of extraordinary activity when galaxies and their central black holes were growing, rapidly consuming vast amounts of gas in the entropy rich, dense early universe. That epoch has passed. The universe has expanded and cooled. The great reservoirs of gas that fed the quasars have been consumed or dispersed. Most large galaxies today have central black holes that are quiet or nearly so. We live in the quiet aftermath of a more energetic age, a universe that has largely burned through its most productive phase and now coasts its most dramatic events, recorded in the light of objects so distant that seeing them means looking backward in time. The universe was louder when it was young. Every observation of a distant quasar is also an act of time travel. Light moves fast, 300,000 kilometers every second, the fastest speed that anything in the universe can achieve. But the universe is vast enough that even at that speed, light takes time, enormous amounts of it, to cross the distances between galaxies. When astronomers observe a quasar whose light has traveled 13 billion years to reach us, they are not seeing that quasar as it exists now. They are seeing it as it existed 13 billion years ago, when the universe was very young, when the galaxy hosting it was still assembling itself from primordial gas, when the black hole at its center was in the full fury of its growth phase. What that quasar looks like today, if it still exists in recognizable form, if its host galaxy has merged with others, if its central black hole has quieted As Sagittarius A star has quieted, we cannot know by looking at it. The light carrying that current information will not reach us for another 13 billion years. We see the past, only the past. Everywhere we look in the universe, we are looking backward in time, by amounts proportional to the distance of what we observe. The night sky is not a view of the universe as it is. It is a layered record of the universe, as it was at different moments at different distances, a composite portrait assembled from light that left its sources at different points in cosmic history. You are right now looking at something ancient wherever you are tonight, and whatever you can see above you. The light from a quasar 13 billion light-years away left its source before the Earth existed, before the Sun ignited, before the solar nebula had begun to collapse, before the molecular cloud that would eventually form our solar system had even condensed from the surrounding interstellar gas. That light has been traveling through the universe since before any of this existed. Through the expansion of space, which stretched its wavelengths and reddened it as it traveled. Through the tenuous intergalactic medium occasionally absorbed or scattered by intervening gas clouds. Through the gravitational fields of countless galaxies, it passed near its path bent slightly by each one. And it arrived here at a telescope on a mountain, or in space, guided by mirrors and detectors, recorded in data analyzed by people who spent years learning how to read it. That light is older than our planet, older than our star. It carries information about a time when the universe looked nothing like it does now, when galaxies were still forming, when the first heavy elements were still being synthesized in the first generation of stars, when the large-scale structure of the cosmos was still assembling itself under gravity's patient direction. Every photon from a distant quasar is a message from before the beginning of our story, an envoy from a universe that did not yet contain us, arriving in a universe that does. There is a kind of tenderness in receiving a message that old, from a source that did not know anyone would be here to receive it. The universe stores what it knows in light. Every photon that has ever been emitted carries within it the conditions of its origin, the temperature of the surface that emitted it, the velocity of the object it came from, the composition of the material through which it passed. These are encoded in its wavelength, its polarization, the subtle patterns of absorption lines imprinted by intervening atoms. Light is the universe's primary medium of record. And black holes, though they swallow light, have generated more recorded light than almost any other class of object, through the blazing of accretion disks, the glow of jets, the superhot corona above the disk, the distorted images of gravitational lensing. The photons we collect from black hole systems carry detailed records of conditions that cannot be replicated in any laboratory. The X-rays from an accretion disk tell us the temperature and density of material spiraling at a fraction of the speed of light. The radio waves from a jet tell us the strength and geometry of magnetic fields millions of light-years from their source. The gravitational lensing patterns tell us the mass distribution of objects too dark to see directly. Each observation is an act of translation, taking light that encoded information in one place and time, and decoding it here and now. Black holes do not give themselves away easily, but they leave traces in everything around them, and light, patient and fast, carries those traces across whatever distance separates the source from the observer. The universe always leaves evidence. We simply have to learn how to read it. The universe keeps its records, and we are part of that keeping. When a photon from a distant quasar enters a telescope and strikes a detector, something changes. The photon is absorbed. Its energy is converted to an electrical signal. The information it carried is extracted and stored in a format that can be analyzed, shared, built upon. The photon has completed a journey of billions of years and billions of light years. It has expanded, with the universe reddened as space stretched beneath it. Bent around gravitational fields survived the vast emptiness of intergalactic space. And at the end of all of that, it lands on something we built, and we read what it has to say. There is a continuity in that, a thread connecting the moment of emission in a young, turbulent galaxy billions of years ago to a quiet moment of observation in a laboratory or on a mountaintop where someone reads the data and understands something new about the universe. The quasar did not know it was being observed. The photon carries no intention, and yet the chain of events that began with a black hole consuming gas in the early universe ends billions of years later with understanding, with a mind assembled from stardust, receiving a message from before it existed. The universe makes observers out of its own material, and then those observers turn and look back at the universe, and the universe through them becomes aware of itself. That loop matter, becoming mind observing matter, is perhaps the quietest wonder of all. Even right now as you rest, ancient light is moving through you. Not metaphorically. Photons, from distant quasars, from ancient galaxy clusters, from the afterglow of the Big Bang itself. The cosmic microwave background radiation that fills all of space uniformly are passing through the room you are in, through the walls, through the air, through your body, continuously, and without pause. The cosmic microwave background alone delivers roughly 411 photons per cubic centimeter of space, everywhere in the universe, at every moment. The space inside your body right now contains thousands of these ancient photons light, left over from the early universe, when it was roughly 380,000 years old, and still glowing with primordial heat. They pass through you because they interact so weakly with ordinary matter. Your atoms are mostly empty space, and these photons slip through the gaps, rarely encountering an electron or a nucleus that absorbs them. Neutrinos from the sun pass through you too, roughly 65 billion of them per square centimeter per second, streaming outward from the solar core, passing through the Earth as if it were not there. And gravitational waves, those ripples in space-time from merging black holes, pass through you continuously as well, stretching and compressing the distances between your atoms by amounts immeasurably small but real. You are not separate from the universe's ongoing processes. You are inside them. They pass through you, around you, and have done so since the moment you were born. The universe has never stopped touching you. The gravity of black holes reaches far beyond what their darkness suggests. At the largest scales of the universe, matter is not distributed randomly. It is arranged in a vast cosmic web, thin filaments of galaxy clusters, stretching across hundreds of millions of light years, surrounding great, empty voids, where almost nothing resides. This structure, called the cosmic web, is the largest pattern in the observable universe. The formation of that pattern was driven by gravity operating over billions of years on the tiny density fluctuations present in the early universe. Dark matter provided the initial scaffolding. Ordinary matter fell into the gravitational wells dark matter created. Galaxies formed at the intersections of the filaments where matter was densest. And at the center of each galaxy, as it formed and grew, a black hole assembled itself, growing through mergers and accretion, influencing the gas supply available to the galaxy, regulating star formation through feedback from its jets, winds. The supermassive black holes at galaxy centers are not passive passengers in the cosmic web. They are active participants, their growth histories shaped by the web, their feedback in turn shaping the galaxies that host them, which are themselves nodes in the larger structure. Gravity connects all of it. The same force that bends light around a stellar mass black hole in the Milky Way operates at every scale, from the orbit of a star near Sagittarius A star to the motion of galaxy clusters separated by hundreds of millions of light years. One force, every scale, all of it connected. Between the great filaments of the cosmic web lie the voids. Not empty, the universe contains almost nothing that is truly empty, but nearly so. The cosmic voids are regions where the average density of matter is far below the cosmic mean. Few galaxies reside there. The gas is thin and cold. The gravitational fields are weak by the standards of the surrounding structure. The largest voids span hundreds of millions of light years. Within them, the universe is as close to silent as it ever gets. No active star formation, no bright quasars, no dense galaxy clusters. Just a tenuous scattering of matter expanding slightly faster than average, because there is less gravity to slow the expansion. These voids are not accidents or absences. They are the complement of the filaments matter that was drawn away from these regions over billions of years, pulled by the gravity of the denser structures surrounding them, leaving behind the emptiness we observe. A void is the record of matter that left. And even in these most silent regions, the universe is not entirely still. Occasional galaxies drift through the voids, small, isolated, quietly forming stars far from any cluster. Dark matter halos thread the void with invisible structure, and primordial black holes, if they exist, would be distributed everywhere in the voids as much as in the filaments, drifting unseen through the quietest regions of the cosmos. Silence in the universe is rarely absolute. There is almost always something there, moving slowly through the dark, carrying the thread of existence through the most patient stretches of space. In the voids, in the filaments, in the spaces between stars within galaxies, the universe carries something that weighs almost nothing and travels at the speed of light and fills every corner of space equally. The cosmic microwave background is the oldest light we can observe, the afterglow of the moment, roughly 380,000 years after the Big Bang, when the universe first became transparent to light. Before that moment, space was filled with a hot, dense plasma that scattered photons continuously. Light could not travel freely. After that moment, the plasma cooled enough for electrons and protons to combine into neutral hydrogen atoms, and space became clear. The light released at that moment has been traveling ever since, stretching as the universe expanded, cooling from a temperature of roughly 3,000 degrees to just 2.7 degrees above absolute zero today. It fills space uniformly in every direction. It is the background against which everything else in the universe is set, and it contains, encoded in tiny temperature fluctuations of less than 1 part in 100,000, the seeds of all the structure that followed: the filaments, the voids, the galaxy clusters, the black holes at their centers. The largest structures in the observable universe were written in embryonic form into the cosmic microwave background 380,000 years after the beginning. We can read that record today precisely with instruments sensitive enough to measure temperature differences smaller than the warmth of a single breath at the distance of the moon. The universe wrote its plan early in light. We are only now learning to read it. A black hole, for all its complexity, can be completely described by 3 numbers. Not an approximation, not a simplified model. A complete, exact description, as precise as anything in physics, captured in just 3 quantities: its mass, its spin, and its electric charge. Mass tells you how much it weighs in the most general sense, how strongly it curves space-time, how far its gravitational influence reaches, how large its event horizon is. Spin tells you how fast it rotates on a scale from perfectly still to the maximum allowed by general relativity. Electric charge in practice is almost always negligibly small for astrophysical black holes. Any charge they acquire is quickly neutralized by attracting oppositely charged particles from the surrounding environment. So in reality, 2 numbers do most of the work. Everything else, the specific star that collapsed to form it, the chemical composition of every gas cloud it ever consumed, the history of every merger it survived, the details of every photon that crossed its horizon, all of that complexity is gone from the outside description, swallowed and compressed into those 2 or 3 quiet numbers. This is called the no-hair theorem, a playful name for a profound result. A black hole has no distinguishing features, no individual characteristics, no texture or pattern that records its history. All the richness of what it consumed is reduced to mass, spin, and charge, like a name that tells you nothing of the life behind it. That simplicity carries something almost philosophical within it. The no-hair theorem says that two black holes with identical mass, spin, and charge are in every physically meaningful sense identical. There is no experiment you could perform from outside the event horizon that would distinguish one from the other, no measurement that would reveal whether one formed from the collapse of a single massive star and the other from the merger of two smaller black holes and the accretion of 1 billion years of gas clouds. The histories are erased. The identities are gone. Only the summary remains. Outside the event horizon, only mass, spin, and charge exist, 3 quiet numbers, like the final line of a very long story, compressed into a single sentence. And yet those 3 numbers reach outward and shape everything around them. The mass curves space across vast distances. The spin drags the surrounding space-time into rotation. Even the charge, when present, creates an electromagnetic field that extends beyond the horizon. Everything the black hole is from the outside is expressed through these 3 quantities. Nothing is hidden, but nothing else is available. The richness is inside, sealed by the horizon. The outside receives only the sum. There is something here that resonates beyond physics. The way a person seen only briefly from a distance can be known only by the most general qualities, the deepest structures, the things that reach farthest outward. What extends beyond the boundary is always simpler than what lies within. Stars consumed, gas clouds dissolved, light forever redirected, ancient collisions absorbed. All of it becomes 3 numbers. The no-hair theorem is in one reading a statement about memory, specifically about what the universe chooses to preserve and what it allows to be lost. Once something crosses the event horizon, its individual character, the precise arrangement of its atoms, the patterns that made it what it was rather than something else, no longer exists in the external universe's accounting. What remains is contribution to mass, spin, and charge. The specific is absorbed into the general. The individual becomes part of the sum. This is exactly what makes the information paradox so troubling. If a black hole evaporates through Hawking radiation, and the radiation carries no record of what fell in, then information is not merely hidden inside the horizon, it is destroyed. The universe loses the ability to reconstruct what was swallowed, even in principle. And if information can be destroyed, something deep about the nature of physical reality is different from what quantum mechanics insists it must be. The 3 numbers hold the summary. Whether they also hold the full history encoded in some form, we cannot yet read. That question sits at the center of the information paradox, unanswered, patient. Everything ever consumed by a black hole is held in those numbers, or it is gone. We do not yet know which. The universe holds some things tightly and does not easily say whether it is keeping them or simply keeping quiet. Of the 3 properties a black hole possesses, mass is the one that reaches farthest. Spin affects the geometry of space in the region immediately surrounding the black hole. The frame dragging effect diminishes with distance, becoming negligible far from the horizon. Electric charge creates fields that extend farther, but are quickly screened by surrounding plasma. Mass is different. The gravitational influence of a black hole falls off with distance, but never reaches 0. At any finite distance from any black hole anywhere in the universe, the gravitational pull of that black hole is present, diminished by distance, but present. This means that the only thing a black hole shares unconditionally with the universe beyond its horizon is its mass. Through gravity, it reaches out and touches everything. Not visibly, not loudly, but with the silent, constant, uncancelable influence of curved space-time. The event horizon is the ultimate boundary of information. Nothing from inside can cross it outward. But mass crosses it, in a sense, through the curvature of space-time it generates. The black hole's presence is felt beyond the horizon, even though nothing from within can reach beyond it. It is a strange kind of communication, one-directional, impersonal, unstoppable. The black hole cannot send a message. It cannot signal its interior state, but it cannot hide its mass, because mass is not inside the black hole in the way that information is. Mass is a property of the space-time geometry itself. What you are at the most fundamental level shapes the space around you, and that shaping cannot be concealed. Between falling in and flying free, there is a place where light circles forever. At a distance of exactly 1.5 times the Schwarzschild radius, 1.5 times the radius of the event horizon, there exists a spherical surface called the photon sphere. Here, the curvature of space-time is precisely balanced against the natural tendency of light to travel in straight lines, and a photon moving at exactly the right angle will circle the black hole in a perfect orbit. In principle, a photon entering this orbit exactly would circle forever. In practice, the orbit is unstable. The slightest perturbation, any tiny deviation from the perfect trajectory, and the photon either spirals inward toward the event horizon or escapes outward to infinity. There is no stable middle path. From a distance, the photon sphere has a visible consequence. It contributes to the bright ring seen in black hole images. Photons that nearly fall in looping once or multiple times around the black hole before escaping produce a series of nested bright rings just outside the main image, each successive ring composed of photons that circled one more time, arriving from more extreme angles, carrying information about the geometry of space extremely close to the horizon. These additional rings are called photon rings, and their precise structure is a fingerprint of the black hole's mass and spin, a signature written in light that curves around darkness. The photon sphere is a threshold of its own kind, not between existence and non-existence, as the event horizon is, between circling and escaping, between staying and going, a boundary defined entirely by geometry. Imagine following that photon. It approaches the black hole at exactly the right angle, not too steep, not too shallow, precisely the trajectory that leads to the photon sphere. It enters the orbit. It begins to circle, once, twice, 3 times, curving through the warped space, its path, a closed loop around a darkness it cannot enter and cannot leave. In this orbit, the photon is not inside the event horizon. It is outside it in normal space, following a path that general relativity permits. But the path leads nowhere. It does not arrive. It does not escape. It simply continues in a perfect circle defined by the geometry of the space around the black hole. From the outside, such a photon would never be seen to escape. From inside the orbit, from the photon's perspective, if photons had perspectives, there would be no sense of being trapped. The path continues. The speed is constant. There is no wall, no cage, no force applying pressure. Just curved space doing what curved space does, redirecting the path of whatever moves through it. The photon circles because that is where the geometry leads. It has not been captured. It has simply found the one trajectory where the universe allows it to stay without falling or fleeing. A photon in the photon sphere is not lost. It is poised at the precise boundary between two futures, traveling at the speed of light and going nowhere. There is a quiet strangeness in that, moving at the ultimate speed, arriving nowhere, forever in between. The difference between a photon that circles forever and one that escapes is not large. It is not a question of speed. All photons move at the same speed. It is a question of angle, the precise direction of travel relative to the curvature of space-time at that location. A photon entering the photon sphere region at an angle fractionally steeper than the critical value spirals inward. A photon entering at an angle fractionally shallower escapes outward. The difference between these two futures is a matter of fractions of degrees, a difference in trajectory so small it approaches the limits of what can even be meaningfully defined. And yet that tiny difference determines everything about the photon's future. One is absorbed by the singularity. One escapes to travel across the universe. Same location, same speed. A hair's breadth of difference in direction. The universe resolves these cases without hesitation. There is no ambiguity in the physics. Each photon follows the path that its exact trajectory demands with perfect precision, because the geometry of space-time is exact. What looks from a human perspective like a razor-thin boundary, a distinction too small to meaningfully represent, is for the physics absolutely deterministic. Each case has one outcome, and the outcome follows inevitably from the initial conditions. The apparent fragility of the boundary is an artifact of our perception. For the universe there is no fragility, only geometry doing its work, sorting each trajectory into its future with perfect consistency. The universe is, in this sense, unhesitatingly decisive about things we find impossibly fine. That balance between falling and circling is not unique to black holes. Every orbit is a version of that same poise, an object moving fast enough that its natural tendency to fall toward a massive body is continuously redirected into a curved path that keeps it at a roughly constant distance, falling but always missing. The forward motion and the downward pull in permanent negotiation. The moon is falling toward Earth. It has been falling for 4.5 billion years, moving forward fast enough that the curve of the Earth drops away beneath it at the same rate that it falls, so the distance stays roughly constant. The Earth is falling toward the Sunday. Every planet in the solar system is in a state of continuous free fall around the Sun. Their trajectories precisely balanced between the pull of the Sun's gravity and the speed of their orbital motion. Every satellite in orbit above Earth is falling continuously. The International Space Station is in free fall. Its occupants float not because there is no gravity, but because they and the station are falling together. And when everything falls at the same rate, the floor provides no force. The photon sphere around a black hole is simply the most extreme version of this universal situation. Every orbit from the Moon to the most distant planet to the innermost stable orbit around a black hole is the same negotiation between falling and going, between gravity and motion. Everything in orbit is in a sense continuously choosing to miss what it is falling toward. And in that perpetual missing, all the structure of the universe is maintained. Right now, the Earth is falling toward the Sunday. It has been falling for roughly 4.5 billion years, and in all that time, it has never arrived. The orbital speed of the Earth, roughly 30 kilometers per second, is exactly sufficient to ensure that as it falls toward the Sun's surface curves away beneath it at the same rate. The Earth's path bends continually toward the Sun, but the Sun is round, and so the bending follows the curvature, and the Earth keeps going around and around, never reaching, never flying free. This is not a delicate situation that could easily have been otherwise. The orbital parameters that keep Earth at a stable distance from the Sun were set during the formation of the solar system, when the disk of gas and dust that surrounded the young Sun settled into orbits governed by angular momentum, gravity. The Earth formed in a region of the disk where the conditions allowed a stable orbit to persist. But the universe contains places where orbits are not stable. Near a black hole at certain distances, the curvature of space-time is so extreme that no stable circular orbit exists. Below a certain radius, 3 times the Schwarzschild radius for a non-spinning black hole called the innermost stable circular orbit, any object that strays inward will inevitably spiral into the event horizon, with no stable orbit to catch it. Closer to the black hole than that, falling is not a risk. It is a certainty. The grace of Earth's orbit, the particular speed and distance that keeps life possible, is not guaranteed everywhere. Here the balance holds. And because it holds, we are here to notice it. There is something worth pausing at in the image of an orbit. An object in a stable orbit is not being held in place. It is not resting. It is not at equilibrium in the way a ball at the bottom of a bowl is at equilibrium. It is in continuous motion, continuously accelerating toward the body it orbits, continuously redirected by that acceleration, continuously moving forward at exactly the speed that makes the falling safe. It is dynamic stillness, motion that produces constancy, change that produces stability. The Earth has not stayed at its current orbital distance because nothing has changed. It has stayed because the changes have balanced the forward motion and the gravitational pull in continuous, precise dialogue over 4.5 billion years. This is the deep structure of orbital mechanics, and it echoes through the universe at every scale. Stars orbit galaxy centers. Galaxy clusters orbit each other. The cosmic web has its own large-scale flows, with galaxy clusters moving through space along the filaments in motions that are the gravitational orbits of the largest structures. Everything is moving. Everything is falling. Everything is in some form of that continuous negotiation between going and arriving. And in those negotiations across every scale, from a photon barely escaping the photon sphere to the orbit of a galaxy cluster through the cosmic web, a kind of grace operates. Not grace in a mystical sense. Grace in the sense of precision, the exact rightness of a motion that sustains itself, that keeps the balance, that falls without landing. It is enough, perhaps, simply to notice that you exist in the middle of it. Some physicists have asked a question that sounds impossible at first, and then refuses to go away. What if the universe we inhabit is itself the interior of a black hole? The idea is not mainstream. It is not accepted by consensus. But it is taken seriously by a small number of physicists working at the intersection of cosmology and quantum gravity, because the mathematics that describes the interior of a black hole and the mathematics that describes the early universe share a striking family resemblance. Both begin from a singularity, a point of extreme density where the known laws break down. Both expand outward from that point. Both are bounded by a horizon that limits what can be seen from within. The Big Bang from outside a hypothetical containing black hole might look like a gravitational collapse, matter and energy falling inward past a horizon, and from inside that horizon, expanding outward as a new space-time. If this were true, the universe would be nested. Our Big Bang would be the interior view of a black hole that formed in some larger universe. And black holes within our universe would each be from inside their own expanding spacetimes, perhaps seeding new universes, each with their own physics, their own constants, their own eventual black holes spawning further interiors. Universes inside universes, without end, without an outermost edge, without a beginning that is truly a beginning. It remains speculative. The idea has not produced testable predictions that distinguish it from alternatives. But it is a reminder that the map we carry is small, and the territory it attempts to describe may be larger than the map has room to represent. The discomfort of that idea, its refusal to be easily dismissed or easily confirmed, is itself a kind of data. Throughout the history of physics, the questions that proved most productive were often the ones that made the existing framework uncomfortable. The question of what happens to the ether when light moves through it led to special relativity. The question of why electrons in atoms did not spiral into the nucleus led to quantum mechanics. The question of what happens at the singularity inside a black hole has not yet led anywhere definitive, but it has generated decades of serious inquiry, and the inquiry has not been wasted. Even wrong attempts at solving a hard problem leave deposits, mathematical tools, conceptual frameworks, ways of thinking that prove useful elsewhere. The struggle with the black hole singularity has produced insights into the nature of quantum information, the relationship between gravity and thermodynamics, and the structure of space-time at the smallest scales. The universe does not make its deepest questions easy to answer. It does not offer them as puzzles with neat solutions waiting to be found. It offers them as genuine unknowns, places where the best available thinking reaches its limit, and the next step requires something that does not yet exist. Being at that edge is not a failure. It is the most honest position in science to know exactly how far the current understanding reaches, and to be clear-eyed about where it stops. The window is small. The light through it is real. And just beyond the glass, something waits that we have not yet found the words for. If black holes could contain their own expanding interiors, their own spacetimes, their own eventual galaxies and stars, then the universe would be recursive in a way that makes the imagination fold back on itself. Each black hole in our universe would be from a perspective we could never access, a kind of beginning. A moment of collapse that from inside looks like expansion. A horizon that from within is simply the edge of the observable, the limit of what light has had time to cross since the beginning of that interior universe. Our own observable universe has a horizon of its own, the cosmic horizon, the distance beyond which light has not had time to reach us since the Big Bang. Beyond that horizon, space continues, we simply cannot see it. We are surrounded by our own observational boundary, which limits our view without limiting the universe. If the nested black hole idea has any truth to it, then the similarity between our cosmic horizon and the event horizon of a black hole is not coincidence. They would be, in some deep mathematical sense, the same kind of boundary seen from different sides. And every black hole we observe would be simultaneously a darkness from outside and an expanse from within. The thing that swallows is also the thing that opens. The darkness from one perspective, the entire sky from another. This may be wrong. It is almost certainly incomplete. But it is beautiful in the way that only ideas at the frontier of knowledge can be beautiful, not polished, not certain, not safe, just reaching. The equations of general relativity describe a black hole with perfect precision. Run them in reverse time in the solutions, and they describe something else. Not a black hole which swallows matter and concentrates it, but a white hole which expels matter outward and from which nothing can enter. A white hole is the time reverse of a black hole. Matter and light pour out of its horizon, and nothing from outside can cross inward. Where a black hole's future is inward and downward toward the singularity, a white hole's past is the singularity, the point from which everything emerges. White holes have never been observed. There is no known physical process by which one would form. They are solutions to the equations, mathematically valid, physically mysterious, with no confirmed counterpart in the observable universe. But here is what makes them quietly remarkable. The Big Bang, as described by the standard cosmological model, resembles a white hole in its mathematics. Matter and energy emerging from a singularity expanding outward, with nothing from outside able to have entered because there was no outside. Whether the Big Bang was in some sense a white hole is a question that physicists have asked without arriving at a consensus answer. The equations permit both. The equations were written to describe gravity without knowledge of what the universe would do with them. And the universe, as it turns out, may have found uses for the mathematics that the mathematician could not have anticipated. Sometimes the equations know the territory better than the explorer does. There is a symmetry at the heart of black hole physics that feels like something the universe is quietly insisting upon. The same mathematical framework, the Einstein field equations, those 10 coupled nonlinear differential equations completed in 1915, describes both the collapse of matter into a black hole and the expansion of the universe from its initial state. The same geometry, the same language, the same structure. Run time forward from a singularity, the universe expands. Run time backward into a black hole, matter collapses to a singularity. The equations are in a deep sense symmetric between these two processes. This does not mean they are the same physical event. The contexts are different. The boundary conditions are different. The surrounding space-time is different. But the structural resemblance is not coincidence. It reflects the fact that both processes are extreme cases of the same underlying physics, gravity, operating at the limits of density and curvature. Einstein did not design the equations to describe black holes or the Big Bang. He designed them to describe gravity. The fact that they encompass both, that they speak equally fluently about beginnings and endings, about collapse and expansion, about the smallest and the largest, that generality was not planned. It emerged from the mathematics. The equations turned out to contain more than their author put into them. This happens sometimes in physics. A framework is built to solve one problem, and then reveals itself to be a window onto something much larger, a language more fluent than the speaker realized, describing more of reality than was intended. The equations spoke. The universe confirmed. A black hole holds what it takes with perfect silence, not metaphorically. The event horizon is by construction the surface from which no signal can emerge. No light, no radio wave, no gravitational wave, no particle, nothing generated within the horizon can cross outward. The interior is causally disconnected from the exterior universe. Whatever the black hole swallows, whatever history, whatever arrangement of matter, whatever encoded information it holds without revealing, the exterior universe cannot know what is inside, because the inside cannot communicate with the outside. This is the deepest kind of silence. Not the silence of emptiness, or the silence of distance, or the silence of a signal too faint to detect. The silence of a boundary that the laws of physics themselves enforce, with no exception at every moment, for every particle and every photon. What is held inside is held completely. There is something about that completeness, that absolute physics-enforced keeping, that takes on a quality beyond the merely physical. When you sit with it long enough, the universe contains, at the center of its most extreme objects, a silence that cannot be broken from within. Not because breaking it is difficult, not because the technology does not yet exist, but because the geometry of space-time itself prevents it permanently without appeal. Some things are kept not by force but by structure, not by walls but by the shape of the space around them. What the horizon holds, it holds not by choosing to. It holds because that is what a horizon is. The event horizon marks the universe's most absolute boundary, and it is invisible. No light emanates from it. No radiation is emitted at the horizon itself. Hawking radiation originates near the horizon, in the quantum fluctuations of the surrounding vacuum, not at the surface of any physical object. The horizon is not a thing you could touch or see or feel as you crossed it. It is a feature of the geometry, a surface defined by the relationship between location, mass, and the speed of light. It is real in the most physically meaningful sense. It has consequences. It affects the trajectories of particles and photons. It divides the universe into two causally disconnected regions. And yet, it has no surface, no texture, no marker. It is woven into the structure of space-time in a way that makes it locally undetectable, while globally absolute. You cannot see the horizon from inside, because all light inside moves inward. You cannot see it from outside, because no light from the horizon reaches you. It exists at the precise location where the outward speed of light is exactly cancelled by the inward pull of gravity, where a photon directed outward makes no progress, suspended at the boundary between escape and capture. That boundary is real. It enforces itself without any mechanism, without any force, without any physical object at that location. The most absolute boundary in the known universe is enforced by nothing but geometry. What the shape of space prohibits completely. To cross the event horizon is to cross a boundary that announces nothing. A boundary that does not ring, does not glow, does not change the air, or alter the light in any locally detectable way. One moment, you are outside. The next, if the black hole is large enough that tidal forces at the horizon are gentle, you are inside, and everything external to you continues to look in your immediate surroundings almost the same. The stars are still visible. The laws of physics still hold locally. The space around you is still in the immediate vicinity, approximately flat. But something has changed that cannot be undone. Your future, which previously contained many directions and many possibilities, now contains only one inward, toward the center. The geometry of space-time inside the event horizon is such that the direction toward the singularity is not a direction in space, it is the direction of the future. You cannot avoid it any more than you can avoid moving forward in time. Outside the horizon, you can choose to accelerate outward or orbit or move in any direction. Inside, all futures lead inward. The singularity is not a place you fall toward. It is a moment you fall into the future. From inside, the horizon terminates at the singularity, the way the future outside terminates at whatever the next moment brings. A threshold crossed without announcement. An irreversibility that felt like nothing when it happened. The universe sometimes changes everything in a moment that feels like any other. There is something about that image, a boundary that cannot be perceived in the moment of crossing that carries a resonance beyond physics. The event horizon is not unique in this quality. The universe is filled with thresholds that announce themselves only in retrospect, boundaries that were crossed without ceremony, transitions that felt continuous from the inside, but were in some meaningful sense discontinuous in their consequences. The moment a star first ignites, when the pressure and temperature at the core of a collapsing gas cloud first reach the threshold for sustained nuclear fusion, there is no explosion, no visible announcement from outside. The star simply begins quietly producing the first photons that will eventually escape its surface millions of years later. The moment a planet first becomes geologically stable enough to allow liquid water to persist on its surface, no ceremony, no line drawn in the rock. The moment life first arose from chemistry, whatever that moment was, wherever it occurred, nothing announced it. The first self-replicating molecule did not glow or vibrate differently. It simply was, and then it replicated, and the universe had crossed a threshold it had not crossed before. Transitions of enormous consequence are often unmarked from within. The universe does not wave flags at its most important moments. It simply crosses them continuously, quietly, and the significance is only visible from afterward, from the changed future that follows what felt in the moment, like any other instant. The event horizon is simply the most extreme example of this pattern. Consequence without ceremony. Change without announcement. A future made irrevocably different by a crossing that felt like nothing at all. Quiet thresholds are everywhere once you begin to look for them. The moment before sleep arrives, not the moment you choose to sleep, but the moment sleep actually comes, is a threshold you cross every night without ever perceiving the crossing. You are awake and then you are not, and the transition between those states has no detectable seam from the inside. The moment understanding settles, when something you have been turning over slowly suddenly resolves into clarity, does not announce itself with a sound or a sensation. It simply arrives, and then it is there, and you cannot quite remember the exact instant of its arrival. The moment a relationship becomes something it was not before. The moment a decision becomes irreversible. The moment grief shifts almost imperceptibly towards something that can be carried differently. These are the quiet event horizons of a human life, thresholds real enough to matter, profoundly invisible enough to be crossed without noticing. General relativity describes the event horizon with mathematical precision. The human equivalents resist that precision. But the structural resemblance is not merely poetic. A threshold is defined by what it changes about the future, not by what it announces in the moment of crossing. The event horizon of a black hole changes everything about the future, of whatever crosses it, with no local announcement. The quiet thresholds of a life do the same. The universe at every scale favors transitions that are felt only after the fact changes that become visible in what follows, not in what was felt at the moment. Perhaps the most important crossings always feel from inside like just another moment. At the edge of what is known, scientists do something that looks from the outside like staring into darkness. They take the most carefully constructed frameworks available: general relativity, quantum field theory, thermodynamics, information theory, and push them toward the conditions near a black hole where those frameworks strain and occasionally contradict each other, and they watch carefully to see where the seams appear. The seams are the most valuable part. A place where two reliable theories produce incompatible answers is not a sign that both are wrong. It is a sign that both are incomplete and that the incompatibility marks the location of the next, deeper understanding. Black holes are extraordinarily useful in this way. They are the universe's laboratory for extreme physics conditions of density, temperature, gravity, and space-time curvature that cannot be reproduced anywhere on Earth, that cannot be simulated in any computer with sufficient fidelity, that can only be approached through mathematics and observation. Every genuine paradox in black hole physics, the information paradox, the singularity, the tension between Hawking radiation and unitarity, is a gift. Not a comfortable one, but a gift, a precise location where the current map is wrong, where the next map must be different, where the understanding that comes after will be richer than the understanding that preceded it. The darkness of a black hole is in this sense productive. It is not merely the absence of light. It is the presence of questions clear enough and sharp enough to guide the next century of physics. The edge of the map is not the end of the territory. It is where the interesting territory begins. Every generation of scientists has inherited a set of questions they did not create and will not fully resolve. The ancient astronomers who first mapped the motions of the planets did not know what planets were made of, or why they moved as they did, or what the sun was, or how far away the stars were. They mapped what they could see with the tools they had, and passed the questions they could not answer to the next generation. Newton inherited those questions, and answered some of them: gravity, the laws of motion, the mathematics of orbits, and in answering them revealed new questions that he could not answer. What is gravity really? What happens at very high speeds? What is the nature of space itself? Einstein inherited those questions and answered some of them: general relativity, the equivalence of mass and energy, the curvature of space-time, and in answering them, revealed new questions. What happens at the singularity? How does gravity fit with quantum mechanics? What is dark energy? Now those questions are inherited by the physicists working today, who are answering some of them and revealing others. The process does not converge toward a final answer. It expands each answer, opening more questions than it closes the territory of the known growing, while the boundary between the known and unknown grows with it. This is not frustrating. It is the structure of inquiry itself, the way that genuine understanding, as opposed to the illusion of understanding, always produces more to wonder about, not less. The questions deepen. The wondering does not stop. And that, quietly, is the most hopeful thing about the whole enterprise. There are questions about black holes that may never be answered, not because the questions are poorly formed, not because the instruments are inadequate, or the mathematics is underdeveloped, or the researchers are insufficiently dedicated, but because the answers may exist only inside the event horizon, permanently sealed from the external universe by the same physics that makes the black hole what it is. What happens at the singularity, the precise physical state of matter and space-time at the center, may be forever inaccessible to any observer outside. No signal can emerge from within the horizon to carry that information outward. No probe sent in could ever report back. The interior of a black hole is, in the most physically rigorous sense, permanently outside the observable universe for anyone who does not fall in. This is a new kind of limit. Not a practical limit like the difficulty of building a better telescope. Not a temporary limit like the state of mathematics in an earlier century. A fundamental limit imposed by the structure of space-time itself. The universe contains regions that are causally disconnected from us, not because they are far away, but because the geometry between us and them prevents any information exchange, now or ever. There are true facts about the universe that we will never know, not because no one has looked carefully enough, because the looking is geometrically impossible. The universe is not obligated to make itself fully visible to the things that live within it. It holds some things for itself, and that permanent privacy is not a failure of science. It is a feature of the universe we inhabit. To study something that may permanently withhold its deepest secrets is an unusual position for a scientist to be in. Most scientific questions, even the hardest ones, carry the implicit assumption that the answer exists and is in principle accessible, that given enough time, enough data, enough cleverness, the truth can be reached. The scientific method is built on that assumption. Observation, hypothesis, prediction, test, revision. Black holes challenge that assumption at its foundation. For questions about their interiors, the test step is physically impossible. No observation from outside can directly reveal what is inside. No experiment can be conducted that would return results to the outside universe. And yet the study continues, and it is productive. Not because the interior will be directly observed, but because the constraints on the interior, the consistency requirements, the thermodynamic laws, the quantum mechanical principles, provide indirect information. If the interior must be consistent with quantum mechanics, then certain things must be true about the exterior, about the Hawking radiation, about the information content of the evaporation. The interior speaks to the exterior through constraints, not through signals, but through the requirement that the universe be self-consistent, that the laws hold everywhere, that the accounting balance. This is, in a way, how many important things are known. Not by direct observation, but by inference, by reasoning from what can be seen to what must be true of what cannot. Some truths are known by their shadows. Some interiors are known by their edges. The boundary tells us something about what it contains, even when the contents are sealed. The universe does not owe us its secrets. This is not a resignation. It is a recognition, an honest acknowledgement of the relationship between the universe and the beings it has produced. We are inside it. We are made of it. We think with matter that was once inside stars, and we look outward with eyes that evolved to navigate a small patch of one planet's surface, and we ask questions about the most extreme objects in existence. The universe did not design us for this. It did not produce in us instruments perfectly calibrated for understanding itself. We are accidental observers, the byproduct of billions of years of physical and biological processes that were driven by chemistry and selection, not by epistemology. And yet here we are, asking, building instruments, writing equations, shipping hard drives from Antarctica, listening for the tremor of a collision a billion light years away. The universe did not give us this capacity as a gift. We grew into it slowly through the same processes that grew everything else, through the accumulation of complexity, through the slow elaboration of information processing systems that began as simple chemical reactions and arrived, after a very long time, at the ability to wonder about black holes. That the wondering is possible at all, but the matter of the universe has arranged itself, in at least this one location, into something capable of asking where the map runs out, is not something the universe planned. It is something the universe allowed, and we have so far chosen to use the allowance. The silence of a black hole and the silence of a sleeping mind are not the same silence, but they rhyme. Both are silences that contain something. A black hole's silence conceals the history of everything it has ever swallowed: mass, spin, charge. And behind those three numbers, a hidden complexity that may or may not be preserved, that may or may not be recoverable, that may or may not be carried outward in the slow warmth of Hawking radiation across timescales longer than the current age of the universe. A sleeping mind contains the accumulated experience of a life, the memories, the unresolved questions, the images from the day just past, processed and reorganized in ways that neuroscience is only beginning to map. What happens in sleep is not nothing. It is, in its own way, a kind of integration, the day's input folded into the larger structure of what is known and remembered and felt. Both silences are doing something. Both are active in their stillness. The universe does not distinguish between the vast and the intimate when it comes to the question of what silence contains. The black hole at the center of the galaxy and the quiet of a mind at rest are both instances of the same general principle, that silence in a physical universe is never truly empty. It is always the surface of something deeper. What appears still is often working. What appears absent is often present in a form that takes more patience to perceive. The quiet is full. It has always been full. You are resting inside a full quiet right now. The universe is vast. That word is used often, and it loses its weight with repetition, but it is worth trying one more time to feel it. The observable universe extends roughly 46 billion light-years in every direction from Earth. It contains an estimated 2 trillion galaxies. Each galaxy contains, on average, hundreds of billions of stars. Each of those stars may host planets. And at the center of most large galaxies sits a supermassive black hole, ancient and still, having grown through billions of years of accretion and merger. The number of black holes in the observable universe is unknown, but the number of stellar mass black holes in the Milky Way alone is estimated in the hundreds of millions. Across 2 trillion galaxies, the total may be incomprehensibly large. Each one is a place where the laws of physics reach their limits. Each one is a place where space-time curves so steeply that the future has only one direction. Each one is a place where the universe keeps something sealed, where silence is not empty, but structured, where 3 numbers encode a history that cannot be read from outside. And all of those black holes across all of those galaxies, across all of that space, all of them are operating right now, accreting or resting, spinning or still, emitting their imperceptible warmth of Hawking radiation into the cold of space, right now, while you breathe, while you rest. The universe is not waiting for anything. It is already fully underway in every direction, at every scale, and you are here inside it, aware of it, which is remarkable. From inside that universe, on one small planet circling one ordinary star, in one of 2 trillion galaxies, something happened that may be in its own way as extraordinary as any black hole. Matter became curious. Not all matter, not even most matter. A tiny fraction of the universe's mass, arranged by chemistry and time into nervous systems of increasing complexity, developed the capacity to ask questions about the rest of the matter, to look outward and wonder, to build instruments and theories and collaborations, and to point them with increasing precision at the most extreme and distant and puzzling things in existence. We do not know if this has happened elsewhere. The universe is large enough that it almost certainly has the same chemistry that produced life on Earth, operates according to the same physical laws everywhere, and the universe has had enough time and enough planets. But we have not confirmed it. We have not yet heard from anyone else who is also asking. So, for the moment in the portion of the universe, we can verify this. Small arrangement of matter on this small planet is the only confirmed location where the universe has looked at itself through eyes capable of understanding what a black hole is. That is not a reason for pride. It is a reason for something quieter and more durable. It is a reason to keep asking, to keep building the instruments and writing the equations and shipping the hard drives from Antarctica and listening for the tremor that traveled 1 billion light-years to reach us. The universe allowed this. We can choose to continue it. Wondering is its own kind of gravity. It pulls things together. Researchers across continents, generations of scientists building on what came before, the data from a telescope in Antarctica combined with data from a telescope in Hawaii to produce an image neither could produce alone. It bends paths that would otherwise travel straight. A student who might have chosen a different field, drawn by a question they could not stop thinking about. An engineer spending years designing a mirror precise enough to feel the tremor of a merger 1 billion light-years away. It reaches across distance, the wondering of a mathematician in 16th century Europe, contributing to the framework that describes a black hole, photographed in the 21st century. The wondering of a physicist in wartime sending a letter from a trench enclosing a solution to equations published weeks before by someone he had never met, and like gravity, wondering never fully stops. It diminishes with distraction, grows fainter when tired, but it does not reach zero. It persists in the background at a low frequency, like the pressure waves from the Perseus cluster, moving through everything at a rate too slow to feel directly, but too steady to disappear. You carry it too. Whatever brought you here tonight to this particular video at this particular hour, in whatever country you're in, whatever you're doing while you listen, something in you was reaching toward questions. Toward the large, the old, the strange, the beyond. That reaching is real. It is yours. And it connects you quietly to everyone who has ever looked up and wondered what the dark contains. Tonight, wherever you are, Sagittarius A star is somewhere in your sky. Not visible, it never is, to human eyes, hidden as it is behind the dust and gas of 26,000 light-years of galactic plane. But it is there, always somewhere above you or below you or beside you, just beyond the horizon, or hidden in the blue of the daytime sky, patient and dim and ancient. 4 million solar masses, an event horizon wider than our solar system, spinning in the dark at the center of everything we call home. And around it, orbiting in their tight and fast ellipses, the stars trace their paths, blue and young and bright, circling something they cannot see, held by a gravity that bends their futures without touching them. Just as the Earth circles the Sunday, just as the moon circles the Earth, just as everything that orbits is falling continuously and continuously missing, which is how all the sustained and beautiful things in the universe maintain themselves. The center of the Milky Way is there tonight, quietly holding 400 billion stars in their places, carrying the history of the galaxy's formation in its mass and spin, flickering, occasionally briefly, when a small cloud of gas drifts close enough to be heated, and then returning to its long, untroubled calm. You are connected to it, not metaphorically. Through gravity which does not stop at any distance, you and Sagittarius A star are in a relationship as old as the solar system, a pull almost immeasurably small at this distance, but real. The universe holds you in its structure. It always has. Let the facts go now. Let the numbers and the names dissolve into something softer. What remains after all of it is simpler than any equation. There are places in the universe where gravity curves so deeply that even light cannot find its way back, where time slows to something barely moving, where the future has only one direction and silence is not empty but full of history, full of mass, full of everything that crossed the threshold and was held. And there is here, this room, this breath, this particular arrangement of ancient atoms that was once inside stars, that carries in its iron the memory of a supernova, that looks outward with eyes made of the same matter it is trying to understand. You are part of what the universe made. And tonight, for a little while, you let some of the universe's larger questions move through you, the way ancient light moves through you, the way gravitational waves move through you, the way the cosmic microwave background fills the space inside this room and passes through the walls and continues outward into the dark, all of it passing through, all of it real. Even as you rest now, the center of the galaxy is turning slowly in the dark 26,000 light-years away, holding everything together with the same quiet gravity it has always used. The black holes are spinning, the accretion disks are glowing, the gravitational waves from ancient mergers are moving through the universe at the speed of light, carrying news of collisions that happened before the Earth existed. And you are here, breathing, resting, made of the same ancient material as all of it. The universe is vast, and you are small within it, and both of those things are true at the same time. And somehow that is not frightening, but settling the way it is settling to remember that you are held inside something much larger than anything you need to manage tonight. Let the black holes keep their silence. Let Sagittarius A star keep its slow watch at the center of the galaxy. You can rest now. I hope you sleep well and dream softly. Good night.